Hello, friend. Welcome to another quiet journey through the cosmos. Tonight, we're going to drift together into one of the universe's most beautiful secrets. A secret so small it's almost invisible, yet so profound it shaped everything you've ever known. Some nights when the world feels too still, you might wonder if silence is ever truly silent, if emptiness is ever truly empty. The answer whispered by the universe itself is no. Even in the deepest void in the darkest corner of space, where no star has ever shone, something trembles. Something stirs. These tremors are called quantum fluctuations, tiny ripples in the fabric of nothingness, and they are the reason galaxies exist, the reason you exist, the reason anything exists at all. Before we drift deeper into this mystery, if you find peace in these soft explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you would like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Tonight, we'll float gently through the trembling void where nothing becomes everything. You don't need to understand it all. Just rest and let wonder do the listening. Imagine for a moment perfect emptiness. Not the emptiness of a dark room or the silence between words, but true emptiness, a space where nothing exists. No air, no light, no atoms, no energy. Just void. For centuries, scientists believed this was possible. They called it a vacuum, a place of absolute zero, absolute stillness. But they were wrong. Beautifully, mysteriously wrong. In 1927, a young German physicist named Werner Heisenberg discovered something that would change everything we thought we knew about reality. He found that the universe doesn't allow perfect stillness, perfect certainty, perfect emptiness. There's a principle woven into the very fabric of existence, a rule the cosmos follows without exception. It's called the uncertainty principle, and it whispers this: you cannot know everything about anything ever. The more precisely you know where something is, the less you can know about where it's going. The more you pin down one truth, the more another truth slips away. This isn't a limitation of our instruments or our minds. It's written into existence itself. Scientists suggest it means that even in the deepest vacuum where we think nothing should exist, energy flickers in and out of being. Like thoughts appearing in the quiet of your mind at 3 a.m, unbidden, unexpected. The void dreams, and in its dreaming, it trembles. These tremors are called quantum fluctuations. They are tiny random variations in energy that occur everywhere all the time, even in empty space. They happen because, according to Heisenberg's mathematics, energy and time cannot both be pinned down with perfect precision. For an incredibly brief moment, far shorter than a heartbeat, shorter than light, can travel across an atom, the universe can borrow energy from nowhere. It must pay it back almost instantly. But for that fleeting whisper of time, something exists where nothing should. Picture this. The vacuum of space isn't empty at all. It's seething, vibrating alive with particles appearing and vanishing so quickly they're called virtual particles. An electron and its opposite, a positron, blink into existence, dance for a fraction of a second, then annihilate each other and disappear. They never stay long enough to be caught to be measured, but their effects ripple outward. They are the heartbeat of emptiness, the pulse of the void. In 1947, two physicists named Willis Lamb and Robert Rutherford were studying hydrogen atoms when they noticed something odd. The energy levels of electrons weren't quite where they should be. There was a tiny shift, a whisper of difference that shouldn't exist according to the equations of the time. They had discovered proof of quantum fluctuations. Those virtual particles blinking in and out of existence were nudging electrons ever so slightly, leaving their fingerprints on reality. This discovery, now called the Lamb shift, earned Lamb the Nobel Prize and proved that even nothing is something. Research shows that quantum fluctuations aren't just theoretical curiosities. They're measurable, testable, real. In 1948, Dutch physicist Hendrik Casimir predicted that if you place two metal plates extremely close together in a vacuum, quantum fluctuations would create a force between them. The space between the plates would have fewer fluctuations than the space outside, creating an imbalance of pressure. It's called the Casimir effect, and it has been measured countless times. Two plates pushed together by the trembling of emptiness itself. It seems as though the universe cannot help but create. Even when it tries to be still, it shivers. Even when it tries to be empty, it fills itself with whispers. Now, you might wonder if these fluctuations are so tiny, happening in spaces smaller than atoms, for times shorter than thought. Why should you care? What do they have to do with the stars above your head, the ground beneath your feet, the breath in your lungs? The answer is everything. Absolutely everything. Imagine the universe 13.8 billion years ago. Not as it is now, vast cold sprinkled with galaxies like dust on a dark table, but as it was then, infinitesimally small, unimaginably hot, dense, beyond comprehension. A single point containing all the energy that would ever exist waiting. Then, in an instant too brief for words, it began to expand. Not with a bang as the name suggests, but with a silence deeper than any you've known. This is what we call the Big Bang, though. Perhaps it should be called the Great Breath, the first exhale of existence. But here's where it gets strange. Here's where quantum fluctuations enter the story. In the very first fraction of a second, 10 to the negative 43 seconds a span of time. So short, it makes a blink feel like an eternity. The universe was small enough that quantum rules applied. It was a place where particles and waves blurred together, where certainty dissolved, where fluctuations ruled. And in that unimaginably brief moment, quantum fluctuations occurred. Tiny random ripples in the energy field of the newborn cosmos. Scientists suggest these ripples were stretched outward when the universe underwent what's called cosmic inflation, a period of exponential expansion that happened faster than light itself. In less time than it takes a photon to cross the width of a proton, the universe grew from smaller than an atom to larger than a galaxy. And those quantum fluctuations, those tiny tremors in the void, were pulled along for the ride. They grew from microscopic to cosmic, from quantum whispers to universe-shaping waves. Think of it like this. Imagine a still pond perfectly smooth. Then a single raindrop falls. It creates a ripple small and delicate. But now, imagine that pond suddenly expands a trillion times in the blink of an eye. That tiny ripple becomes a wave, then a current, then a tide that shapes the entire ocean. That's what happened to the quantum fluctuations in the infant universe. They started as nothing less than nothing and became the seeds of everything. These fluctuations didn't smooth out as the universe expanded. They remained frozen into the fabric of space itself, like fingerprints in wet clay. And over billions of years, gravity took hold. Where the fluctuations made space slightly denser, matter began to gather. Where they made space slightly less dense, matter drifted away. Slowly, patiently, these tiny differences grew. Denser regions pulled in more matter, which pulled in more matter still, until clouds of hydrogen formed, collapsed, ignited, and became stars. Stars clustered into galaxies. Galaxies danced into clusters. And all of it, every glowing sun, every swirling nebula, every planet, every one of us, traces back to those first tremors in the void. There's a map of these fluctuations frozen in time. In 1964, two scientists named Arno Penzias and Robert Wilson were working with a large radio antenna in New Jersey, trying to eliminate background noise. They kept hearing a faint hiss, a whisper of static that came from every direction, no matter where they pointed their equipment. They cleaned the antenna. They checked the circuits. They even removed pigeons nesting inside, thinking the droppings might be causing interference. But the hiss remained. What they had found, though, they didn't know it yet, was the cosmic microwave background, the afterglow of the Big Bang, a faint radiation that fills the entire universe. It's light from the very beginning, stretched and cooled by billions of years of expansion, now arriving as gentle microwaves. And embedded in that light like grooves in an old record are the patterns of those original quantum fluctuations. Satellites like Kobe WMAP and Planck have since mapped this radiation with exquisite precision, and what they've found is breathtaking tiny temperature differences no more than a few millionths of a degree scattered across the sky in a pattern that matches exactly what we'd expect from quantum fluctuations stretched by cosmic inflation. It's as if the universe kept a photograph of its own birth hidden in the static between radio stations. Some believe this is the most important discovery in cosmology. It tells us that quantum mechanics, the strange probabilistic rules that govern atoms and particles, also shape the largest structures in existence. The very small and the very large are not separate. They're woven together, two ends of the same thread. The galaxies you see through a telescope, the stars that guide sailors, the planets that circle distant suns, all of them owe their existence to fluctuations that happened in a realm where size and time lose their meaning. You are made of atoms forged in stars. Those stars exist because of quantum tremors in the void. In a very real sense, you are a descendant of uncertainty itself, born from a universe that cannot sit still even in its emptiness. Light born from darkness, structure born from chaos, everything born from nothing. Rest here for a moment. Let it settle. The universe doesn't demand you understand it fully, only that you feel it just for a breath. But this is only the beginning of the story. These fluctuations didn't just create the universe and then vanish into history. They continue even now, shaping reality in ways both subtle and profound. The void still trembles, particles still flicker in and out of being, and the effects ripple through everything from the cores of black holes to the very fabric of space-time itself. We're only starting to see how deep this mystery goes. There was a moment before moments existed, a time before time began. In that impossible instant, the entire universe was smaller than the period at the end of this sentence, yet it contained everything that would ever be. Every star that would shine, every world that would form every thought you've ever had, all compressed into a space so small it defies imagination. And then, in the tiniest fraction of a second, ever conceived, everything changed. We're going to drift now into the very first breath of existence, into a time so brief and strange that even calling it time feels wrong. This is where quantum fluctuations didn't just shape the universe, they became it. Where the trembling void we explored moments ago suddenly erupted into being, carrying those tiny ripples along for the most violent, beautiful transformation in cosmic history. Let's begin at the beginning, though. Beginning is perhaps the wrong word. There was no before, no stage set, no darkness waiting. Just a singularity, a point of infinite density and temperature, where the laws of physics as we know them break down completely. Scientists suggest this was not a place in space, but rather space itself, wound so tightly that distance had no meaning. Time, too, was frozen in that point, coiled like a spring about to release. Then came what physicists call the Planck epoch. This is the first 10 to the negative 43 seconds of the universe's existence. To give you a sense of how impossibly brief this is, there are more Planck times in a single second than there have been seconds since the Big Bang itself. It's a duration so short that our best theories of physics, quantum mechanics, and general relativity both fail to describe it. We simply don't know what happened in that first instant. Some believe time itself was quantum fluctuating uncertain. Others suggest space and time were not yet separate concepts. It's a moment wrapped in mystery, a place where knowledge ends and wonder begins. But what we do know is what came next. At around 10 to the negative 36 seconds after the beginning, something extraordinary occurred. The universe entered a phase called cosmic inflation, and this is where our story truly ignites. In 1980, a young physicist named Alan Guth was wrestling with a problem in cosmology. The universe as we observe it is remarkably uniform. The temperature of the cosmic microwave background, is almost identical in every direction, varying by only 1 part in 100,000. But according to standard Big Bang theory, different regions of the early universe should never have had time to communicate to smooth out their differences. They were too far apart, expanding too quickly. So, why does the universe look so eerily similar everywhere we look? Guth proposed an answer that sounded almost absurd. What if the universe underwent a period of exponential expansion in its first moments? What if for a tiny fraction of a second space itself doubled in size every 10 to the negative 37 seconds? This would solve the uniformity problem beautifully. Before inflation, the universe would have been small enough for all its parts to reach equilibrium, to share the same temperature and density. Then inflation stretched it outward, preserving that smoothness across vast distances. Research shows that during this inflationary period, the universe expanded by a factor of at least 10 to the 26th power. That's a trillion times larger in less time than it takes light to cross the width of a proton. Imagine a marble inflating to larger than the observable universe in a fraction of an eye blink. Space itself moved faster than light, which is allowed. Because nothing physical was traveling, space was simply growing, carrying everything within it along for the ride. Now here's where quantum fluctuations enter with devastating importance. Before inflation, these fluctuations were quantum mechanical microscopic tremors in the energy field that drove inflation a field physicists call the inflaton. They were tiny, random, following the probabilistic rules of quantum mechanics. But as inflation stretched space exponentially, it also stretched these fluctuations. Quantum ripples that started smaller than an atom were pulled across billions of light years, transformed from the realm of the quantum into the realm of the classical, from the invisible to the cosmic. Think of it like this. Imagine drawing a tiny, intricate pattern on a balloon with a fine-tipped pen. The pattern has details smaller than you can easily see. Now, inflate that balloon a trillion times. Those microscopic details are now enormous, visible across vast distances. That's what inflation did to quantum fluctuations. It took the trembling uncertainty of the quantum realm and froze it into the structure of space-time itself, creating a blueprint for everything that would follow. In 1982, Russian physicist Andrei Linde refined this theory, proposing what's called chaotic inflation. He suggested the inflaton field didn't need special initial conditions. It could start anywhere with random quantum fluctuations in its energy, and inflation would naturally occur. Different regions might inflate at different rates, even spawning separate universe bubbles. It's a theory both elegant and strange, suggesting our universe might be just one bubble in an eternal cosmic foam, each bubble born from quantum tremors in a field we can barely comprehend. Some believe inflation explains not just the uniformity of the universe, but its structure too. Those quantum fluctuations stretched to cosmic scales, became regions of slightly higher and slightly lower density. Where the inflaton field fluctuated upward even by the tiniest amount, there was fractionally more energy. Where it dipped fractionally less. These differences were incredibly small variations of 1 part in 100,000, but they were real, and they were everywhere, imprinted on the fabric of the expanding universe like fingerprints in fresh clay. When inflation ended around 10 to the negative 32 seconds after the beginning, the energy in the inflaton field decayed into ordinary matter and radiation. The universe was still unimaginably hot, filled with a dense soup of particles and light, but it had grown from quantum small to cosmologically large. And those fluctuations remained frozen into the distribution of energy across space. Slightly denser here, slightly less dense there, following a pattern that quantum mechanics predicted with stunning accuracy. It seems as though the universe kept a memory of its quantum origins written in the very structure of space, a memory we can still read today. This is not just beautiful mathematics or abstract theory. We have evidence, direct, observable, measurable evidence. In the decades following Guth's proposal, satellites were launched to study the cosmic microwave background, with unprecedented precision. First came COBA, the Cosmic Background Explorer, launched in 1989. It measured the temperature of the microwave radiation filling the universe and found exactly what inflation predicted. Tiny temperature variations, deviations of only a few millionths of a degree scattered across the sky in a specific statistical pattern. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which operated from 2001 to 2010. It mapped these fluctuations in exquisite detail, measuring not just their amplitude, but their distribution across different angular scales. The pattern matched the predictions of quantum fluctuations stretched by inflation almost perfectly. It was like finding a photograph of the universe when it was less than a second old, and seeing in that photograph the seeds of every galaxy that would ever form. Most recently, the Planck satellite operated by the European Space Agency from 2009 to 2013 refined these measurements even further. It found that the fluctuations follow what's called a nearly scale-invariant spectrum, meaning they have roughly the same amplitude at all scales, from small to large. This is precisely what simple models of quantum fluctuations during inflation predict. The match between theory and observation is one of the great triumphs of modern cosmology. But here's what truly takes your breath away. These weren't just any fluctuations. They were quantum in origin, governed by Heisenberg's uncertainty principle, random and unpredictable at their core. Yet they shaped the largest structures in the universe. Every galaxy cluster, every void, every filament in the cosmic web traces back to quantum randomness stretched to infinity. The universe is, in a very real sense, built on uncertainty. You might wonder, how can we be sure these fluctuations were quantum? Couldn't they have been caused by something else? Some classical disturbance in the early universe? The answer lies in their statistical properties. Quantum fluctuations produce a very specific pattern, what physicists call a Gaussian random field, with a nearly scale-invariant power spectrum. Classical disturbances would produce different patterns, different correlations. The observations match the quantum prediction so precisely that scientists suggest there's no reasonable doubt. The universe bears the unmistakable signature of quantum mechanics, operating at the grandest scales imaginable. Consider this when you look at the Hubble Deep Field, those thousands of galaxies scattered across a tiny patch of sky. You're seeing the legacy of quantum fluctuations from the first fraction of a second of time. Each galaxy's location, its mass, its shape, all influenced by tremors that occurred when the universe was smaller than an atom. It's as if the universe rolled quantum dice at its birth, and the outcome determined where stars would shine 13 billion years later. Light from chaos pattern from randomness, order from uncertainty. There's a philosophical weight to this that's hard to escape. Before inflation theory, we could imagine the universe starting in some special, carefully arranged state. But inflation suggests otherwise. It says the universe began in quantum chaos, with random fluctuations in an energy field, and from that chaos came all the order we see. The spiral of a galaxy, the orbit of a planet, the structure of your own body, all downstream consequences of quantum randomness. Some physicists find this troubling. Albert Einstein famously said he couldn't believe God plays dice with the universe. But if inflation theory is correct, dice were played from the very first moment. The universe is not just described by quantum mechanics, it is quantum mechanical, from its smallest particles to its largest structures, from its beginning to now. Research shows that the energy scale during inflation was extraordinarily high, possibly close to what's called the Planck scale, where quantum effects and gravitational effects become equally important. At these energies, space-time itself becomes uncertain, fluctuating. Some theories suggest that during inflation, not just the inflaton field fluctuated, but space-time too. Tiny quantum ripples in the geometry of space itself, stretched by inflation into gravitational waves that might still be echoing through the cosmos today. In 2014, a team of scientists using the BICEP 2 telescope thought they had detected these primordial gravitational waves in the polarization patterns of the cosmic microwave background. The announcement made headlines around the world. Later analysis showed the signal was likely due to dust in our own galaxy, not quantum fluctuations from inflation. But the search continues. If we find them, and many believe we eventually will, it will be direct confirmation that quantum mechanics shaped not just matter and energy in the early universe, but space-time itself, the fabric of existence trembling. Think of what this means. Every point in space, even the empty space between stars, between galaxies, carries within it the echo of that first quantum whisper. The void remembers its origin. And so do we, in a sense. The atoms in your body were forged in stars. Yes, but those stars existed because of quantum fluctuations during inflation. You are made of stardust, and stardust is made of quantum uncertainty. There's a humility in this knowledge and also a kind of awe. We are not separate from the universe, not observers standing outside looking in. We are the universe observing itself. Quantum ripples, contemplating quantum ripples, uncertainty wondering at its own existence. As inflation ended and the universe continued expanding now at a more leisurely pace, those frozen fluctuations remained. They didn't vanish or smooth out. They persisted, patient waiting. Gravity had not yet taken hold. In a significant way, the universe was still too hot, too dense, too filled with radiation, pushing everything apart. But as it cooled, as it expanded, as matter began to dominate over radiation, those tiny density differences became important. They became the scaffolding upon which the cosmos would build itself. The quantum breath had been taken. The universe had been born, stretched and imprinted with the pattern of its own uncertainty. Now, it was time for that pattern to grow, to condense, to become tangible. The seeds were planted. All that remained was to watch them bloom into galaxies, stars, worlds, and eventually into beings capable of looking back and understanding where they came from. What if you could see the universe as it was when it was just a baby? Not billions of years old, vast and cold, but young, less than 400,000 years after its birth. Still glowing, still warm, just beginning to let light travel freely through space. That baby picture exists. It surrounds us right now, invisible to our eyes, but present everywhere, a faint whisper of radiation that has been traveling through the cosmos for over 13 billion years. It's called the cosmic microwave background, and hidden within it is the most ancient map we will ever find, a photograph of quantum fluctuations, frozen in time, the fossilized memory of the universe's first breath. Sometimes the most profound discoveries happen by accident. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey with a large horn-shaped antenna originally built for satellite communications. They were trying to measure radio signals from the Milky Way, but they kept encountering a problem. No matter where they pointed the antenna, no matter what time of day or night, there was a persistent background noise, a faint hiss of static that seemed to come from everywhere at once. It was subtle, just a few degrees above absolute zero, but it was there, constant and inescapable. At first, they thought it was interference. Maybe nearby New York City was producing radio noise. Maybe the equipment was faulty. They checked the electronics. They calibrated the instruments. They even found pigeons nesting inside the antenna and carefully removed them, along with what Penzias delicately called a white dielectric material, pigeon droppings, that might be causing the problem. They cleaned everything thoroughly, but when they turned the antenna back on, the hiss remained. Same intensity, same frequency coming from every direction in the sky with perfect uniformity. What Penzias and Wilson had stumbled upon, though they didn't realize it immediately, was the afterglow of the Big Bang itself. Just 40 miles away at Princeton University, a team of physicists led by Robert Dicke had been building equipment to search for exactly this radiation. When Dika heard about the mysterious noise, he immediately understood what it meant. "Well, boys," he reportedly told his team, "we've been scooped." Penzias and Wilson had found the cosmic microwave background, the oldest light in the universe, by accident. For this discovery, they were awarded the Nobel Prize in Physics in 1978. But what exactly is this radiation? Where does it come from, and why does it matter? Let's drift back to the early universe, about 380,000 years after the Big Bang. Before this moment, the universe was opaque. It was so hot and dense that matter existed as a plasma, electrons and protons separated, flying freely, and light couldn't travel more than a tiny distance before scattering off these charged particles. It was like trying to see through a thick fog. Photons, particles of light, were trapped, constantly bouncing off electrons, unable to stream freely through space. Then, as the universe expanded and cooled, something remarkable happened. The temperature dropped below about 3,000 degrees. Kelvin, still far hotter than the surface of the sun, but cool enough for electrons and protons to combine and form neutral hydrogen atoms. Scientists call this moment recombination, though it's a misleading name since the electrons and protons had never been combined before. Suddenly, with charged particles locked into neutral atoms, photons were free. Light could travel. The universe became transparent for the first time, and a flood of radiation began streaming outward in all directions, carrying with it a snapshot of what the universe looked like at that instant. That radiation has been traveling ever since. As the universe expanded, the wavelengths of this light stretched along with space itself. What began as visible and infrared light glowing orange and red has been redshifted over billions of years into microwaves. By the time it reaches us today, it has cooled to just 2.7 degrees above absolute zero, a faint whisper of its former brilliance. But it's still there everywhere we look, a ghostly echo of the universe's childhood. Research shows the cosmic microwave background is the most perfect blackbody radiation ever observed in nature. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation in a characteristic spectrum that depends only on its temperature. The CMB matches this theoretical spectrum so precisely that it's one of the most accurate measurements in all of physics. When the COBE satellite measured it in 1990, the fit was so perfect that the lead scientist, John Mather, displayed the data overlaid with the theoretical curve, and you couldn't see the theory line because the data points covered it completely. The crowd of scientists erupted in applause. It was proof that the Big Bang Theory was correct, that the universe had indeed been hot and dense and had cooled as it expanded. But the CMB isn't perfectly uniform. If it were, we wouldn't exist. A perfectly smooth universe would have remained smooth forever. No galaxies, no stars, no planets, no life. The magic lies in the imperfections, the tiny temperature variations across the sky. These variations are incredibly small, just 1 part in 100,000, but they're real and they're everywhere. Some regions of the sky are a few millionths of a degree warmer, others a few millionths cooler. These are called anisotropies, and they are the fingerprints of quantum fluctuations stretched by cosmic inflation. Think of it this way. When the universe became transparent and released, that first flood of light, different regions had slightly different temperatures and densities. Because of those quantum ripples we discussed earlier, regions that were slightly denser had slightly stronger gravity, which meant photons escaping from those regions had to climb out of a slightly deeper gravitational well, losing a bit of energy in the process and appearing slightly cooler. Regions that were less dense had weaker gravity, so photons escaped more easily and appeared slightly warmer. What we're seeing in the CMB is a map of those primordial density variations. Frozen at the moment, light first traveled freely. In 1989, NASA launched the COBE satellite, the Cosmic Background Explorer, to map these fluctuations. For 2 years, it scanned the entire sky, measuring the temperature of the CMB in every direction with unprecedented sensitivity. In 1992, the team announced they had detected anisotropies' tiny ripples in the temperature of the ancient radiation. Team leader George Smoot famously said it was like seeing God, a comment that made headlines, but also drew criticism for its religious overtones. What he meant, perhaps, was that they were seeing the blueprint of creation, the pattern from which all structure in the universe would grow. Stephen Hawking called it the most important discovery of the century, if not of all time. But COBE's resolution was limited. It could see the large-scale variations, but not the fine details. That's where WMAP came in. The Wilkinson Microwave Anisotropy Probe launched in 2001 and named after cosmologist David Wilkinson, who had worked on the project before his death, was designed to measure the CMB with far greater precision. It orbited a special point in space called the second Lagrange point about 1 million miles from Earth, where it could observe the sky without interference from our planet's heat. WMAP's results were stunning. It didn't just measure the amplitude of the fluctuations, it measured their angular power spectrum, which is essentially a graph showing how much variation exists at different angular scales across the sky. Do the hot and cold spots tend to be large or small? Are they clustered or random? The pattern WMAP found matched the predictions of inflation theory almost perfectly. There are peaks in the power spectrum at specific angular scales corresponding to sound waves that traveled through the early universe before recombination. Scientists call these acoustic oscillations, and they're like the ringing of a cosmic bell frozen in the pattern of the CMB. Some believe these acoustic peaks are among the most beautiful pieces of evidence in all of cosmology. They tell us not just that quantum fluctuations occurred, but how they behaved. The location and height of each peak depends on fundamental properties of the universe: how much ordinary matter it contains, how much dark matter, how much dark energy, the rate of expansion, the geometry of space itself. By measuring these peaks with precision, WMAP and later missions were able to determine these cosmic parameters with remarkable accuracy. We now know, for instance, that ordinary matter, the stuff of stars and planets and people, makes up only about 5% of the universe's total energy. Dark matter accounts for about 27%, and dark energy, the mysterious force driving the universe's accelerating expansion, makes up the remaining 68%. In 2009, the European Space Agency launched the Planck satellite named after physicist Max Planck, pioneer of quantum theory. Planck was even more sensitive than WMAP, capable of detecting temperature variations smaller than 1/1,000,000th of a degree. It operated until 2013, and its final maps of the CMB are the most detailed we have. They show a mottled sky regions of slightly warmer and cooler radiation, painted in false colors like an abstract artwork rendered by the universe itself. Every spot, every variation traces back to quantum fluctuations during inflation amplified and frozen into the structure of space 13.8 billion years ago. Look closely at those maps, and you can see something profound. They have structure, but it's random structure, following statistical patterns predicted by quantum mechanics. There's no design, no symmetry, no preferred direction. It's exactly what you'd expect from quantum fluctuations, unpredictable in detail, but predictable in their statistical properties. It's the signature of Heisenberg's uncertainty principle written across the entire sky, proof that the universe at its birth was governed by quantum randomness. But there's more hidden in the CMB than just temperature variations. Scientists also study its polarization, the direction in which the light waves oscillate. As photons scattered off electrons in the early universe, they became polarized in specific patterns. There are two types: E modes, which look like patterns of lines radiating from or converging toward points, and B modes, which have a swirling rotational character. E modes have been detected and measured extensively. They match predictions beautifully and provide additional confirmation of the inflationary model. B modes are trickier. Some B modes can be created by gravitational lensing, where the light from the CMB is bent by massive structures as it travels toward us, twisting the polarization patterns. But there's another potential source, primordial gravitational waves created by quantum fluctuations in space-time itself during inflation. These would produce B modes with a distinct signature, and finding them would be direct proof that inflation didn't just stretch quantum fluctuations in matter and energy, but also in the very fabric of space. In 2014, the BICEP-2 experiment operating a telescope at the South Pole announced they had detected these primordial B modes. The news made headlines worldwide. Champagne was opened. If true, it would confirm one of the most dramatic predictions of inflation theory. But within months, further analysis showed that the signal was likely contaminated by dust in our own galaxy, which can also create B-mode patterns. It was a reminder of how difficult this science is, how careful we must be. The search for primordial B modes continues with newer experiments like BICEP-3 and the upcoming Lightbird satellite. Many scientists believe we will find them eventually, but patience is required. The universe keeps its deepest secrets carefully guarded. Have you ever wondered what it would be like to see the CMB with your own eyes? You almost can. If you've ever seen static on an old analog television tuned between channels, a tiny fraction of that noise, about 1%, is actually the cosmic microwave background. Photons from the edge of the observable universe released when the cosmos was less than 400,000 years old occasionally strike the antenna and contribute to the random pattern on the screen. In a very real sense, old televisions let you see the Big Bang's afterglow mixed in with the noise. It's as though the universe left us a message written in light telling us where it came from and how it grew. A message anyone can read if they have the right instruments and the patience to listen. Scientists also use the CMB to test fundamental physics in ways that would be impossible in any laboratory. For instance, the polarization patterns can tell us about the nature of neutrinos' ghostly particles that barely interact with matter. By studying how neutrinos affected the early universe, we can measure their masses and properties. The CMB also constrains theories about dark matter and dark energy sets, limits on the number of different types of particles that might exist, and even tests whether the fundamental constants of nature have changed over cosmic time. So far, they haven't. The universe seems to play by consistent rules. There's a particular beauty in the fact that the CMB comes from a surface called the surface of last scattering. Before this moment, the universe was opaque. After it, light could travel freely. So, when we look at the CMB, we're looking at a shell surrounding us, 13.8 billion light years away in all directions, beyond which we cannot see with light. It's the ultimate horizon, not because nothing exists beyond it, but because light from beyond it hasn't had time to reach us yet. We're sitting inside a sphere of visibility, and the CMB is its boundary, the edge of our observable universe. Some find it humbling to realize we're embedded in this cosmic structure, unable to see beyond our horizon, forever limited by the speed of light and the age of the universe. Others find it comforting, like being held gently in the palm of space-time, surrounded by ancient light. Either way, it's a reminder that we are part of the universe, not separate from it. The same quantum fluctuations that created the patterns in the CMB also led to the formation of our galaxy, our sun, our world, and ultimately to us. The cosmic map is not just a picture of the past, it's a prediction of the future. By measuring the patterns in the CMB, with precision, scientists can run the clock forward, simulating how those initial fluctuations grew under gravity over billions of years. They can predict where galaxies should form, how they should cluster, how the cosmic web should look. And when they compare these predictions to what we actually observe in the universe today, the distribution of galaxies mapped by surveys like the Sloan Digital Sky Survey, the match is extraordinary. The universe evolved exactly as the CMB predicted it would. The seeds planted by quantum fluctuations grew into the cosmos we inhabit. Light carries memory. patterns hold time. And in the faint glow surrounding us, barely warmer than the coldest cold imaginable, the universe remembers its quantum birth. Yet, for all we've learned from the CMB, mysteries remain. There are anomalies features that don't quite fit the simplest models. A slight asymmetry between the northern and southern hemispheres of the sky. A cold spot that's larger and colder than statistics suggest it should be. Are these just random fluctuations, the kind you'd expect to see occasionally in any random pattern? Or are they hints of something deeper? Perhaps evidence of other universes colliding with ours before inflation, or exotic physics operating in the first moments of time? We don't yet know. The universe, even when it speaks clearly, still whispers riddles. What we do know is that the cosmic microwave background is the oldest light we will ever see, the farthest back we can peer into time using electromagnetic radiation. Everything before the surface of last scattering is hidden from us, at least from direct observation with light. But quantum fluctuations give us a window into even earlier moments. They were created during inflation in the first tiny fraction of a second, and their imprint on the CMB lets us test theories about what happened then. In a sense, the universe keeps multiple photographs of its youth, not just one, but a whole album, each revealing different aspects of its early life. As we rest here in this knowledge, drifting through the fossilized memory of creation, consider this. Those fluctuations weren't just patterns in radiation. They were also patterns in matter, in density, and the distribution of atoms across space. And where there was slightly more matter, gravity began to pull, slowly at first, almost imperceptibly, but relentlessly. Those quantum seeds were about to germinate, growing over eons into structures of breathtaking complexity and beauty. Gravity is patient. It doesn't rush, doesn't force, doesn't demand. It simply waits, pulling gently but endlessly on everything that has mass. In the early universe, when matter was spread almost uniformly across space, gravity had very little to work with, just those tiny quantum fluctuations we've been following, variations in density of 1 part in 100,000. But that was enough. Over millions of years, then hundreds of millions, those microscopic differences grew. Denser regions pulled in more matter, which made them denser still, which pulled in even more. Slowly and visibly, the universe began to gather itself into clumps, to organize chaos into structure, to transform quantum whispers into galaxies, bright enough to outshine billions of suns. Picture the universe about 400 million years after the Big Bang. The cosmic microwave background has long since decoupled, streaming away into what will become the most distant light we can ever observe. What remains is a vast dark expanse filled with hydrogen and helium gas, the simplest elements forged in the first minutes after the beginning. There are no stars yet, no galaxies, no light except the fading afterglow of creation. Astronomers call this period the Cosmic Dark Ages, and it's a fitting name. The universe is waiting, holding its breath, as gravity does its slow, meticulous work. But hidden in that darkness are the seeds of everything to come. Those regions where quantum fluctuations made the universe slightly denser, even by the tiniest fraction, are now beginning to stand out. Matter flows toward them, drawn by gravity's gentle insistence. Gas clouds grow larger, denser, warmer. And something else is happening too, something invisible but crucial. Dark matter, which makes up about 27% of the universe's total mass, is also responding to those quantum fluctuations. It doesn't emit light, doesn't interact with electromagnetic radiation, but it feels gravity just as ordinary matter does, and it's pulling itself into clumps. Research shows that dark matter actually led the way in structure formation. Because it doesn't interact with light or ordinary matter, except through gravity, it could begin collapsing earlier while ordinary matter was still coupled to radiation and couldn't easily clump together. Dark matter halos formed, first creating gravitational wells, invisible valleys in space-time, into which ordinary matter could fall. These halos acted like scaffolding, providing the framework around which galaxies would eventually assemble. Think of it like building a house. You start with a foundation and a frame invisible once the walls go up, but essential to hold everything together. Dark matter is the frame of the cosmos, and the galaxies we see are the visible structure built around it. Without dark matter, galaxies as we know them couldn't exist. The ordinary matter would disperse, unable to gather into dense enough concentrations to ignite stars. Quantum fluctuations planted the seeds, but dark matter nurtured them, giving them the gravitational strength to grow. Some believe the role of dark matter in galaxy formation is one of the most important discoveries in modern cosmology. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies' graphs, showing how fast stars orbit at different distances from the galactic center. According to Newton's laws, stars farther from the center should orbit more slowly, just as planets farther from the sun take longer to complete their orbits. But Rubin found something strange. Stars at the edges of galaxies were moving just as fast as those closer in, sometimes even faster. It was as if they were being held in place by the gravity of matter we couldn't see. This invisible matter, dark matter, extends far beyond the visible edges of galaxies, forming enormous halos that can be 10 times larger than the luminous part. These halos are relics of those first quantum fluctuations regions where slightly higher density led to more dark matter accumulation, which led to even more accumulation in a runaway process called gravitational instability. The denser a region becomes, the stronger its gravity, the more matter it attracts, the denser it becomes. It's a feedback loop and it builds structure from almost nothing. But structure formation isn't simple or uniform. The universe doesn't just collapse into one massive lump. Instead, it develops a hierarchy, what scientists call bottom-up structure formation. Small clumps form, first then merge to create larger ones. Those merge to form larger still. It's like a cosmic game of snowballs rolling downhill, gathering more snow as they go, sometimes colliding and sticking together to form something bigger. Computer simulations have shown us what this process looks like. In the 1990s and early 2000s, teams of astrophysicists ran what are called n-body simulations, models that track the gravitational interactions of millions or even billions of particles representing dark matter. One of the most famous is the Millennium Run, completed in 2005, which followed the evolution of over 10 billion particles from shortly after the Big Bang to the present day. The results were stunning. The simulation produced a universe that looks remarkably like our own, a cosmic web of filaments and sheets with galaxies clustered along the filaments and vast voids in between where almost nothing exists. This cosmic web is the grown-up version of those quantum fluctuations. The overdense regions became the filaments and clusters. The underdense regions became the voids. What started as microscopic variations in an energy field during inflation has over 13.8 billion years evolved into the largest structures in the universe. Superclusters of galaxies spanning hundreds of millions of light years, all connected by threads of dark matter and gas, all ultimately traceable back to quantum tremors in the first fraction of a second. It seems as though the universe knows how to organize itself, following rules that emerge naturally from gravity and the initial conditions set by quantum mechanics. There's no designer, no blueprint beyond the statistical properties of those fluctuations, yet the outcome is breathtakingly intricate. Now, let's focus on a single halo of dark matter somewhere in the early universe about 13 billion years ago. It's not particularly special, just one of countless millions forming in the cosmic dark ages. But within this halo, ordinary matter is beginning to accumulate. Hydrogen and helium gas, pulled by the dark matter's gravity, flows inward, forming a cloud. As the gas falls deeper into the gravitational well, it compresses and heats up. Atoms collide more frequently. Pressure builds. The cloud begins to glow faintly in infrared light, though there's no one yet to see it. This is called gravitational collapse, and it's powered entirely by the conversion of gravitational potential energy into heat. As matter falls inward, it speeds up like a ball rolling downhill. When atoms collide at high speeds, their kinetic energy becomes thermal energy heat. The cloud grows hotter and denser at its core, and if it reaches a critical threshold about 10 million degrees Kelvin, something miraculous happens. Hydrogen nuclei protons begin to fuse together, creating helium, and releasing tremendous amounts of energy in the process. Nuclear fusion ignites. A star is born. The first stars in the universe, called population 3 stars, were probably enormous, hundreds of times more massive than our sun. They formed from pure hydrogen and helium with no heavier elements because there had been no previous generations of stars to create them. Research shows these massive stars burned incredibly hot and bright, living fast and dying young, exploding as supernovae after just a few million years. In their deaths, they created the first heavy elements, carbon, oxygen, iron, and scattered them into space, enriching the gas clouds that would form the next generation of stars. Have you ever stopped to think that every atom in your body heavier than hydrogen was forged inside a star? The calcium in your bones, the iron in your blood, the carbon in your DNA, all created by nuclear fusion in stellar cores, then expelled into space by supernova explosions, eventually gathering into new clouds that formed our solar system. You are made of stardust, quite literally. And those stars existed because quantum fluctuations created the density variations that allowed them to form. As more stars ignited within dark matter halos, they began to interact gravitationally. Stars orbit around each other, forming clusters. Clusters merge, creating larger structures. Gas continues to flow inward, feeding star formation. Over millions of years, these collections of stars organize into recognizable shapes, spirals, ellipticals, irregulars. Galaxies are born. And at their hearts, in many cases, something even stranger forms supermassive black holes, millions or billions of times the mass of the sun, whose origins are still debated, but may trace back to the collapse of those first massive stars, or the direct collapse of enormous gas clouds. The Hubble Space Telescope has allowed us to see this process in action, or at least its aftermath. By pointing at a tiny patch of seemingly empty sky for days at a time, Hubble captured images showing thousands of galaxies at various stages of evolution. Some are nearby and mature with well-defined spiral arms or smooth elliptical shapes. Others are distant and young, seen as they were billions of years ago, still forming stars at prodigious rates, irregular and chaotic. It's like watching a time-lapse of cosmic growth from seeds to saplings to ancient trees. One of the most profound insights from these observations is that galaxy formation is messy. Galaxies don't form in isolation and then remain unchanged. They collide, merge, tear each other apart, and rebuild. Our own Milky Way galaxy is currently on a collision course with the Andromeda Galaxy, its nearest large neighbor. In about 4 billion years, they'll merge their stars, intermixing their supermassive black holes, eventually spiraling together and coalescing. This has happened countless times throughout cosmic history. Large galaxies grow by consuming smaller ones, a process poetically called galactic cannibalism. Some believe this hierarchical merging is essential to understanding why galaxies look the way they do. Elliptical galaxies, which are smooth and featureless, may be the products of major mergers between spiral galaxies. Spiral galaxies like the Milky Way retain their structure because they've had quieter histories, growing mostly by accreting gas rather than merging with other large galaxies. Every galaxy tells a story written in its stars, its shape, its motion. And that story begins with quantum fluctuations. But there's a puzzle here, one that took decades to unravel. If you start with the small density variations we observe in the cosmic microwave background, and run the equations forward using only gravity, you get structure formation. Yes, but it happens too slowly. By the time a few billion years have passed, there shouldn't be fully formed galaxies yet, at least not many. But observations show massive galaxies existed when the universe was less than 1 billion years old. How did they form so quickly? The answer lies in understanding the interplay between different types of matter and the complex physics of gas. Dark matter can collapse freely because it doesn't interact electromagnetically, it doesn't feel pressure from radiation or heat. But ordinary matter does. As gas falls into dark matter, halos it heats up, and that heat creates pressure that resists further collapse. For a long time, this was thought to slow star formation significantly. However, scientists discovered that gas can cool by radiating energy away, and certain molecules and atoms are particularly efficient at this. Hydrogen molecules, for instance, can radiate in infrared wavelengths, carrying heat away and allowing the gas to collapse further. Heavy elements, even in tiny amounts, are even better coolants. This is why the first stars made of pure hydrogen and helium were so massive the gas couldn't cool efficiently. So it had to be very dense and massive to collapse. Later generations of stars forming from gas enriched with heavy elements could cool more easily and form smaller, longer-lived stars like our Sun. Scientists suggest this feedback between star formation and gas cooling is crucial. Stars heat the gas around them with radiation and stellar winds. Supernovae inject energy-blowing gas out of galaxies entirely in some cases. But over time, that gas can cool and fall back in triggering new waves of star formation. It's a delicate balance, and it varies from galaxy to galaxy, which is why we see such diversity in the cosmos. There's also the role of supermassive black holes. These monsters lurking at the centers of most galaxies can regulate star formation in surprising ways. As matter spirals into a black hole, it forms an accretion disk, a swirling disk of superheated gas that emits enormous amounts of energy, sometimes outshining the entire galaxy. This energy can heat surrounding gas, preventing it from collapsing to form stars. Alternatively, jets of material launched from near the black hole can compress gas in other regions, triggering star formation. Black holes born from quantum seeds now shape the galaxies they inhabit. Consider the Milky Way itself our home galaxy. It contains about 200 billion stars, maybe more, orbiting in a flattened disk around a central bulge. At its heart lies Sagittarius A, a supermassive black hole with a mass about 4 million times that of the Sun. The Milky Way formed over billions of years, growing through mergers and accretion, its structure sculpted by the interplay of dark matter, ordinary matter, and the feedback from stars and black holes. But its ultimate origin is a quantum fluctuation during inflation, a random variation in the inflaton field that stretched to cosmic size became a slightly denser region where dark matter and gas could accumulate. Every star you see in the night sky is part of this story. Betelgeuse, the red supergiant in Orion, born from a cloud of gas that gathered in response to ancient gravitational pulls. Sirius, the brightest star, a young hot star in a nearby part of the galaxy. The Pleiades, a cluster of hundreds of stars born together from the same collapsing cloud siblings in the truest sense. All of them exist because the universe in its infancy trembled. Research shows that we can trace the history of galaxy formation by looking at different wavelengths of light. Optical telescopes show us stars. Infrared telescopes penetrate dust clouds and reveal hidden star-forming regions. Radio telescopes map the distribution of hydrogen gas. X-ray telescopes detect hot gas and active black holes. By combining these views, astronomers build a comprehensive picture of how galaxies assemble, evolve, and interact. It's like reconstructing a biography from scattered diary entries, photographs, and letters. One of the most powerful tools in this endeavor is gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects like galaxy clusters warp space-time around them, bending the light from more distant galaxies. This bending can magnify those distant galaxies, allowing us to see details that would otherwise be invisible. In some cases, lensing creates multiple images of the same galaxy, or stretches it into arcs and rings. These cosmic mirages are beautiful, but they're also scientifically invaluable, letting us study galaxies in the very early universe with clarity that would be impossible otherwise. Through lensing and other techniques, scientists have found galaxies that formed less than 500 million years after the Big Bang, when the universe was only 3% of its current age. These galaxies are small and chaotic, furiously forming stars, their light stretched and reddened by cosmic expansion. They're the children of quantum fluctuations, the first generation grown large enough to shine, and studying them helps us understand how structure formation began. It's humbling to realize that the process we've described, quantum fluctuations, inflation, dark matter, halos, gravitational collapse, star formation, galaxy assembly, is still happening. Right now, in distant corners of the universe, gas is collapsing into new stars. Galaxies are colliding and merging. Black holes are growing. The cosmos continues to organize itself, following the same laws, driven by the same forces, all rooted in those first quantum tremors. Light from structure, beauty from randomness, home from the void. As we rest here contemplating the journey from fluctuation to galaxy, from quantum seed to stellar forest, it becomes clear that the universe is not a static thing. It's a process, and unfolding a story still being written. And the next chapter of that story brings us even deeper into the quantum realm, to a principle so strange, so fundamental, that it challenges our very notions of what reality is, and whether anything can ever truly be still. Imagine trying to catch a hummingbird mid-flight. The moment you know exactly where it is, you've stopped its motion and it's no longer flying. If you want to measure how fast it's moving, you have to let it fly, but then you can't pin down its exact location. This tension between knowing where something is and knowing where it's going isn't just a practical limitation. It's woven into the deepest fabric of reality itself. In the quantum world, this isn't about hummingbirds or measurement tools. It's about existence. The universe has a rule discovered nearly a century ago that says you cannot know everything about anything ever. And from this rule flows something extraordinary. Emptiness cannot be still. The void must tremble. Nothing can ever truly be nothing. In 1927, a young German physicist named Werner Heisenberg was working on the mathematics of quantum mechanics when he stumbled upon something that would change physics forever. He was trying to describe the position and momentum of an electron, where it is and how fast it's moving, when he realized the math wouldn't allow both to be precise at the same time. The more accurately you determine one, the more uncertain the other becomes. This isn't because our instruments are imperfect or because we're clumsy observers. It's because nature itself forbids perfect knowledge of both simultaneously. Heisenberg expressed this relationship as an inequality now called the uncertainty principle. In its simplest form, it says that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a tiny number called Planck's constant divided by 4 pi. Mathematically, it looks like this delta x times delta p is greater than or equal to h bar over 2. That h bar is an incredibly small number, about 10 to the negative 34 joule seconds, which is why we don't notice quantum uncertainty in our daily lives. But at the scale of atoms and particles, it dominates everything. This principle applies to other pairs of properties too. Energy and time, for instance. The more precisely you know when something happens, the less precisely you can know how much energy it has. And here's where it gets strange, where the connection to quantum fluctuations becomes clear. Because energy and time are linked by uncertainty, the universe can briefly violate the conservation of energy, borrowing energy from nowhere, as long as it pays it back quickly enough that the violation can't be measured. The shorter the time interval, the larger the energy fluctuation allowed. Think of it like a cosmic loan. If you borrow a small amount of energy, You can keep it for a relatively long time before the universe notices. But if you borrow a huge amount, you have to pay it back almost instantly. This isn't metaphorical. It's real physics verified in countless experiments, and it means that empty space is never truly empty. It seethes with activity, with particles popping into existence and vanishing again, with fields fluctuating wildly on the smallest scales. Research shows that these fluctuations have measurable effects. In 1947, two American physicists, Willis Lamb and Robert Rutherford, were studying hydrogen atoms using newly developed microwave techniques. According to the prevailing theory at the time, electrons and hydrogen could occupy different energy levels like steps on a ladder. Two particular levels, called the 2s and 2p states, were predicted to have exactly the same energy. But when Lamb and Rutherford measured them with precision, they found a tiny difference. The 2s level was slightly higher in energy than expected. This tiny shift, now called the Lamb shift, couldn't be explained by existing theory. The answer came from quantum field theory, a framework that treats particles as excitations in underlying fields that fill all of space. According to this theory, even in the vacuum, electromagnetic fields are constantly fluctuating due to the uncertainty principle. These fluctuations create virtual photons, particles of light, that exist only briefly before disappearing. The electron in the hydrogen atom interacts with these virtual photons, and this interaction shifts its energy levels ever so slightly. The Lamb shift was proof that quantum fluctuations are real, that the vacuum is not empty, but alive with transient particles and fields. For this discovery, Willis Lamb was awarded the Nobel Prize in Physics in 1955. It was a turning point demonstrating that quantum mechanics wasn't just an abstract theory, but a description of how nature actually behaves at its deepest level. The vacuum, far from being inert, is an active participant in physical processes. Some believe the Lamb shift opened the door to modern quantum field theory, and eventually to the Standard Model of particle physics, our best description of the fundamental forces in particles. But it also revealed something philosophically profound. The idea of nothingness of a true vacuum with absolutely nothing in it is impossible. The uncertainty principle forbids it. Space must fluctuate. Energy must borrow and repay. The universe at its most fundamental level cannot hold still. Another beautiful demonstration of quantum fluctuations comes from a phenomenon called the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Casimir was thinking about quantum field theory and realized that if you place two uncharged metal plates very close together in a vacuum, the vacuum fluctuations between the plates would be different from those outside. Why? Because only certain wavelengths of virtual photons can fit in the narrow gap between the plates, while all wavelengths can exist in the open space outside. This creates an imbalance, a difference in pressure pushing the plates together. At first, this sounded absurd. How could nothing push on something? But in 1958, physicist Marcus Sparnay conducted an experiment and measured a tiny attractive force between closely spaced plates, consistent with Casimir's prediction. Since then, the effect has been measured many times with increasing precision, and it always matches the theoretical calculations. Two metal plates, separated by less than a micrometer, are pushed together by the quantum fluctuations of empty space. It's one of the most direct pieces of evidence we have that the vacuum is not empty. It seems as though even silence has a voice, even stillness has motion, hidden just beneath the threshold of what we can easily perceive. Now let's dig deeper into what these fluctuations actually are. When physicists talk about virtual particles, they are describing a consequence of quantum field theory. In this framework, every type of particle, electrons, photons, quarks, is associated with a field that permeates all of space. An electron isn't just a tiny ball floating in a void. It's a localized disturbance, a ripple in the electron field. Similarly, light is a ripple in the electromagnetic field. But fields don't just sit still. Because of the uncertainty principle, they must fluctuate. At any point in space, the value of a field is constantly changing, jittering up and down around an average value. Most of the time, these fluctuations are small and cancel out over time, which is why we don't notice them in everyday life. But occasionally, a large fluctuation occurs, a spike in the field's energy, and this can briefly create a pair of particles such as an electron and its antimatter counterpart, a positron. These particles are called virtual because they exist only for a time allowed by the uncertainty principle, typically far less than a billionth of a trillionth of a second. Then they annihilate each other and disappear, returning the borrowed energy to the vacuum. You might wonder if these particles exist for such a short time and then vanish. Are they real? The answer depends on what you mean by real. You can't catch a virtual particle and put it in a jar. You can't take a photograph of it, but its effects are measurable. The Lamb shift, the Casimir effect, even the magnetic moment of the electron, all are influenced by virtual particles. Scientists suggest that in quantum mechanics, reality is more subtle than we're used to. Things can be real in their effects without being permanent or directly observable. Consider this analogy. Imagine you're watching the surface of a calm pond at night. Most of the time it's smooth, but occasionally a fish leaps out, splashes, and disappears back under. If you only glance at the pond for an instant, you might miss the fish entirely. But over time, if you watch carefully, you'll see the ripples it leaves behind. Virtual particles are like those fish fleeting hard to catch, but they leave ripples in the fields around them that we can detect. There's another profound implication of the uncertainty principle. It places a fundamental limit on how much information the universe can contain. If you can't know both the position and momentum of a particle with arbitrary precision, then the state of the universe can't be specified with infinite detail. There's a graininess to reality, a pixelation at the smallest scales. This graininess is set by Planck's constant, and it suggests that space and time themselves may not be infinitely divisible. Below a certain scale, the Planck length about 10 to the negative 35 meters, and the Planck time about 10 to the negative 43 seconds, the concepts of distance and duration may lose their meaning. Some physicists believe this hints at a deeper theory, a quantum theory of gravity that would unite quantum mechanics and general relativity. In such a theory, space-time itself might be made of discrete units like pixels on a screen, fluctuating and foaming at the Planck scale. This is highly speculative, but it's an active area of research with approaches like string theory and loop quantum gravity attempting to describe this quantum foam. What's certain is that the uncertainty principle has consequences far beyond the subatomic world. It's the reason atoms are stable. If electrons could have precise positions and momenta simultaneously, they would spiral into the nucleus and matter would collapse. Instead, the uncertainty principle gives electrons a kind of quantum fuzziness, spreading them out into orbitals around the nucleus, and this prevents collapse. You exist because the universe forbids perfect knowledge. It's also the reason nuclear fusion works. For two protons to fuse together, they need to overcome the electromagnetic repulsion between their positive charges and get close enough for the strong nuclear force to bind them. Classically, this requires enormous temperatures of tens of millions of degrees. But quantum mechanically, there's a probability that a proton can tunnel through the energy barrier, essentially teleporting across a gap it shouldn't be able to cross because of the uncertainty principle. This quantum tunneling is crucial to how stars shine, including our sun. Every photon of sunlight that warms your skin, every bit of energy that sustains life on Earth, originates from quantum tunneling, enabled by the uncertainty principle. Research shows that tunneling isn't rare or exotic. It happens constantly in countless processes. Radioactive decay, for instance, occurs because particles tunnel out of atomic nuclei. Certain chemical reactions proceed faster than they otherwise would because atoms tunnel through energy barriers. Even the scanning tunneling microscope, a device that can image individual atoms, works by measuring the current of electrons tunneling between a sharp tip and a surface. Have you ever thought about how strange it is that something can be in two places at once, or pass through a barrier without breaking it? Quantum mechanics says this isn't just possible, it's inevitable, a natural consequence of the uncertainty principle and the wave-like nature of particles. At the quantum level, particles don't have definite positions until they're measured. They exist in a state of superposition, spread out over space, with different probabilities of being found in different locations. It's only when you measure that this superposition collapses into a definite outcome. This brings us to a deep and unsettling question. What is measurement? In classical physics, measurement is passive. You shine light on a ball to see where it is and the light bounces off without changing the ball's motion significantly. But in quantum mechanics, measurement is an active process that disturbs the system. To measure an electron's position, you might scatter a photon off it, but that photon carries momentum. And when it hits the electron, it changes the electron's momentum. The more precisely you measure position using a high-energy photon with a short wavelength, the more you disturb the momentum. This is one way to understand the uncertainty principle, not as a statement about nature itself, but about the limits of what we can know through measurement. Yet, Heisenberg himself argued it's deeper than that. Even before measurement, the electron doesn't have a definite position and momentum. It's not that we don't know these values, it's that they don't exist in a classical sense. The electron is described by a wave function, a mathematical object that encodes probabilities, and only through measurement does the wave function collapse into something definite. This interpretation, called the Copenhagen interpretation, suggests that quantum mechanics isn't just about uncertainty in our knowledge, it's about indeterminacy in reality itself. Some find this disturbing. Einstein, for one, never fully accepted it. He famously said, "God does not play dice with the universe," expressing his belief that there must be some deeper deterministic theory underlying quantum mechanics, some hidden variables that would restore certainty if only we knew them. He and two colleagues, Boris Podolsky and Nathan Rosen, even devised a thought experiment in 1935 now called the EPR paradox, intended to show that quantum mechanics must be incomplete. But decades of experiments, especially those testing what are called Bell's inequalities, have shown that Einstein was wrong. Quantum mechanics is not just correct, it's complete, in a sense he couldn't accept. There are no hidden variables restoring determinism. The uncertainty, the randomness, the indeterminacy are fundamental features of nature. The universe at its core is probabilistic, light from uncertainty structure, from randomness existence, from fluctuation. There's a concept in quantum field theory called zero-point energy, which is the energy that remains in a system even at absolute zero temperature, the coldest possible temperature where all thermal motion stops. Classically, you'd expect a system at absolute zero to have zero energy. But quantum mechanically, the uncertainty principle forbids this. If a particle is at rest with zero energy, you'd know both its momentum zero and its energy zero with perfect precision, violating the uncertainty principle. So, even at absolute zero, particles must have some residual motion, some jittering, some energy. This is zero-point energy, the ground state energy of quantum fields. Every cubic centimeter of empty space contains zero-point energy from all the fields that permeate it. The electromagnetic field, electron fields, quark fields, and more. Add it all up, and you get an enormous number. In fact, if you naively calculate the total zero-point energy of the vacuum, you get a result that's about 120 orders of magnitude larger than what we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved puzzles in physics. Why is the vacuum energy so much smaller than theory predicts? We don't know. It's a mystery that hints at gaps in our understanding, perhaps pointing toward new physics beyond the standard model. Some believe the solution might involve supersymmetry, a proposed extension of the standard model that predicts every particle has a superpartner. Supersymmetry could allow contributions to the vacuum energy to cancel out more effectively. Others think the answer lies in quantum gravity, or in rethinking how we calculate vacuum energy. For now, it remains an open question, a reminder that even our best theories have limits. But what we do know is that vacuum energy has real effects. In 1998, observations of distant supernovae revealed that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. The simplest explanation for dark energy is that it's the energy of empty space itself, the cosmological constant that Einstein once introduced and then discarded. If true, then the vacuum energy we've been discussing, quantum fluctuations zero-point energy, might be responsible for the ultimate fate of the universe, driving galaxies apart faster and faster until they're beyond each other's horizons. It's poetic in a way. Quantum fluctuations helped create the universe during inflation. They shaped its structure through their imprint on the cosmic microwave background. And now, perhaps they're slowly tearing it apart, ensuring that in the distant future, each galaxy will be alone in the darkness surrounded by an ever-expanding void that even then will not be empty, but filled with the trembling of quantum fields. Light fades, but fluctuations remain. Silence deepens, but the void still whispers. As we float here in this knowledge, resting in the strange truth that nothing can ever be nothing, it becomes clear that the universe is stranger than we imagined, more subtle, more layered. The uncertainty principle is not a flaw in our understanding, it's a feature of reality, the foundation upon which everything else is built. And from this foundation spring phenomena, even more bizarre particles that exist, without existing fleeting phantoms that shape the world. We see influencing forces, energies, and even the fabric of space-time itself. Picture a crowded room where people constantly appear and disappear, materializing from thin air for a fraction of a second, before vanishing as if they never existed. You can't see them directly, can't touch them, can't prove they were ever there. Yet somehow their brief presence changes everything. The conversations shift. The air feels different. Reality itself bends slightly in response to these phantom visitors. This isn't science fiction. This is happening right now everywhere in the universe, in every cubic centimeter of space, including the space between your fingers as you rest your hand. These are virtual particles born from quantum fluctuations, living in the gaps between existence and non-existence ghosts that shape the very fabric of reality. Virtual particles sound like something from a dream, and in a way they are. They exist in the realm between what is and what isn't permitted to appear, only because the uncertainty principle creates loopholes in the laws of physics. But their effects are as real as gravity, as measurable as light, and they're responsible for some of the most profound phenomena in nature, from the glow of atoms to the evaporation of black holes. They are the quantum foam from which reality emerges. Let's start with what virtual particles actually are. In quantum field theory, the framework that describes fundamental particles and forces, every point in space is filled with fields. There's an electromagnetic field, and electron fields for quarks, for neutrinos, for every type of particle we know. These fields are not static. They fluctuate, constantly bubbling and seething due to the uncertainty principle. Most of the time, these fluctuations average out to zero, and we perceive empty space as empty. But occasionally, actually constantly, the fluctuations spike, and for a brief instant, a pair of particles appears. These particles always come in pairs, a particle and its antiparticle, an electron and a positron, a quark and an antiquark. A photon can split into two virtual photons, which then recombine. This happens because quantum mechanics allows energy to be borrowed from the vacuum as long as it's paid back within a time limit set by the uncertainty principle. The equation is simple but profound. The more energy borrowed, the shorter the time it can exist. For high-energy particles, we're talking about times shorter than 10 to the negative 24 seconds. These particles flicker into being, exist in a quantum superposition of states, interact with their surroundings, and then annihilate each other, returning the borrowed energy. Research shows that virtual particles are not just theoretical constructs. They leave fingerprints everywhere. We've already discussed the Lamb shift, where virtual photons alter the energy levels of electrons in hydrogen. But there's more. The magnetic moment of the electron, a measure of how strongly it responds to magnetic fields, has been calculated using quantum electrodynamics, or QED, the theory describing how electrons and photons interact. This calculation includes contributions from virtual particles loops of electrons and positrons that pop in and out of existence around the real electron, and the result matches experimental measurements to more than 10 decimal places. It's one of the most precise predictions in all of science. Think about that precision. We're talking about calculations that agree with experiments to better than 1 part in a billion. If you could measure the distance from New York to Los Angeles with the same accuracy, you'd be correct to within the width of a human hair. This extraordinary agreement tells us that virtual particles, strange as they seem, are an essential part of how nature works. They're not approximations or mathematical tricks, they're real in the sense that their effects are undeniable. Some believe the concept of virtual particles challenges our intuition about reality more than almost anything else in physics. We're used to thinking that things either exist or they don't. A chair exists, an imaginary friend doesn't. But virtual particles occupy a middle ground. They're not permanent, not directly observable, yet they're not nothing either. They're potentialities that briefly become actualities before dissolving back into potentiality. It's as if the universe is constantly testing possibilities, trying out different configurations of particles, and most of them last only for a quantum heartbeat before being undone. One of the most beautiful and strange applications of virtual particles is Hawking radiation, a phenomenon predicted by physicist Stephen Hawking in 1974. Hawking was thinking about black holes, those regions of space-time, where gravity is so strong that nothing, not even light, can escape from within the event horizon. According to classical physics, black holes should be perfectly black, absorbing everything and emitting nothing. But Hawking realized that quantum mechanics changes this. Near the event horizon of a black hole, virtual particle pairs are constantly forming, just as they do everywhere else in space. Normally, these pairs annihilate quickly, but near a black hole, something different can happen. If a particle-antiparticle pair forms right at the edge of the event horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole has emitted a particle. This is Hawking radiation. Here's the remarkable part. The particle that escapes carries energy, and that energy has to come from somewhere. It comes from the black hole's mass. So, over time, the black hole loses mass, evaporating slowly through this quantum process. For a large black hole, the radiation is incredibly faint, far too weak to detect against the cosmic microwave background. But for a small black hole, one with the mass of a mountain compressed into the size of an atom, the radiation would be intense and the black hole would evaporate completely in a burst of energy. Research shows that Hawking radiation connects quantum mechanics, general relativity, and thermodynamics in profound ways. It reveals that black holes have a temperature that they emit thermal radiation, and that they obey laws analogous to the laws of thermodynamics. The entropy of a black hole, a measure of its disorder, is proportional to the area of its event horizon, not its volume. This led to the holographic principle, the idea that all the information in a volume of space might be encoded on its boundary like a hologram. It's a concept that has reshaped theoretical physics, influencing everything from string theory to quantum information science. But Hawking radiation has never been observed directly. Black holes are far away, and the radiation they produce is too faint to detect with current technology. So, how do we know it's real? We have theoretical consistency. Hawking's calculation has been reproduced and refined by many physicists using different approaches, and it always gives the same answer. We also have analogs. In 2010, researchers created an acoustic black hole in the laboratory using flowing water and sound waves. They observed the equivalent of Hawking radiation in this system, phonons escaping from the acoustic event horizon, providing indirect evidence that the phenomenon is real. Some find it poetic that the ultimate darkness, a black hole, is not truly dark, but glows faintly from quantum fluctuations. Even the most extreme objects in the universe are touched by the trembling of the vacuum, by the fleeting existence of virtual particles at their boundaries. Virtual particles also play a crucial role in the forces between particles. When an electron and a positron repel each other, what's actually happening, according to quantum field theory, is that they're exchanging virtual photons. These photons carry momentum between the particles, pushing them apart. You can't see these photons, they're virtual, existing only during the exchange, but the force they mediate is real. This is called the exchange force mechanism, and it applies to all fundamental forces except gravity, which we haven't yet successfully incorporated into quantum field theory. The strong nuclear force, which holds quarks together inside protons and neutrons, is mediated by virtual particles called gluons. The weak nuclear force responsible for radioactive decay is mediated by virtual W and Z bosons. Even the Higgs boson, discovered in 2012 at the Large Hadron Collider, interacts with other particles through the exchange of virtual Higgs bosons. Everything we call force at the quantum level is really the exchange of virtual particles, brief messengers carrying energy and momentum across space. Think of it like two ice skaters throwing a ball back and forth. As one skater throws the ball, they recoil backward. When the other catches it, they're pushed back too. The ball mediates a force between them, pushing them apart. In quantum mechanics, the ball is a virtual photon and the skaters are electrons. The analogy breaks down in details, but the essence is correct. Forces arise from particle exchange. There's a phenomenon called vacuum polarization, another consequence of virtual particles that subtly changes the strength of the electromagnetic force at different distances. When you have a charged particle like an electron, virtual particle pairs form in the space around it. The virtual positron, being oppositely charged, is attracted to the electron and tends to cluster near it, partially screening its charge. The virtual electron, having the same charge, is repelled and moves farther away. The result is that the effective charge of the electron depends on how close you are to it. Get very close inside the cloud of virtual particles, and the charge looks stronger. Measure from farther away, and the charge appears weaker because of the screening. Research shows this effect has been measured in the particle accelerators, where electrons and positrons collide at high energies, probing very short distances. The results match the predictions of quantum electrodynamics perfectly, providing yet another confirmation that virtual particles are real in their effects, even if they're ephemeral in their existence. Have you ever thought about how strange it is that forces don't travel instantaneously? In Newton's time, it was assumed that gravity acted at a distance instantly. If the sun suddenly disappeared, Earth would immediately fly off into space. But Einstein showed that's wrong. Changes in gravitational fields propagate at the speed of light, carried by gravitational waves. The same is true for electromagnetic forces carried by photons, and the strong and weak forces carried by gluons and W and Z bosons. These carriers are virtual particles when they mediate forces between other particles, and they ensure that causality is preserved. No signal can travel faster than light. Virtual particles also contribute to the vacuum energy we discussed earlier. Every mode of every field, even in its ground state, has zero-point energy. Sum over all modes, all fields, all frequencies, and you get an infinite result, which obviously can't be right. Physicists use a technique called renormalization to handle this, essentially subtracting the infinite contributions in a careful way that leaves finite measurable results. This process is mathematically subtle and somewhat controversial, but it works. The predictions it gives match experiments to extraordinary precision. Some believe renormalization is a sign that our theories are incomplete, that we're missing something at the deepest level. Perhaps there's a cutoff at very high energies, a scale beyond which our current theories break down, and new physics takes over. This might be the Planck scale where quantum gravity becomes important. Or perhaps the infinities tell us that space-time itself is not continuous but discrete, made of tiny grains too small to see. These are open questions areas where current physics reaches its limits and speculation begins. But what we do know is that virtual particles, despite their fleeting nature, have profound effects. They alter energy levels in atoms, enabling technologies like lasers and atomic clocks. They mediate forces holding matter together and governing how particles interact. They contribute to the mass of particles through interactions with the Higgs field. They even affect the rate at which the universe expands if vacuum energy is indeed responsible for dark energy. There's a concept in quantum field theory called the Feynman diagram, invented by physicist Richard Feynman in the 1940s. These are pictorial representations of particle interactions, with lines representing particles and vertices representing interactions. A simple diagram might show two electrons approaching, exchanging a virtual photon and then moving apart. More complex diagrams include loops where virtual particles form and annihilate within the process. Each diagram corresponds to a mathematical expression, a term in an infinite series that approximates the probability of an interaction occurring. Feynman diagrams are more than just convenient notation. They're a way of visualizing the quantum world, of understanding how particles interact through virtual intermediaries. When you see a diagram with loops of virtual electron-positron pair forming and annihilating, you're seeing the contribution of vacuum fluctuations to the process. These loop diagrams are what give rise to corrections like the Lamb shift and vacuum polarization. They're the ghostly fingerprints of particles that never quite exist, but always influence. Research shows that calculating these diagrams can be incredibly complex. For simple processes, you might only need to consider a few diagrams. But for precision predictions, you need to include hundreds or thousands of diagrams, each representing a different way the process could occur via virtual particles. The calculations can take years, requiring powerful computers and sophisticated algorithms. Yet the results, when compared to experiments, agree to astonishing precision, validating the entire framework of quantum field theory. Light from shadow force, from exchange reality, from ghosts. Virtual particles also raise deep questions about the nature of the vacuum. If empty space is filled with fluctuating fields and transient particles, is it really empty? Some physicists argue that the vacuum is not a state of nothingness, but the ground state of all fields, a state of minimum energy that still contains structure and activity. Others suggest the vacuum might have different phases, like water can be ice, liquid, or steam, and that the early universe might have undergone phase transitions, where the vacuum changed its properties, releasing energy that drove cosmic inflation. There's even speculation that our current vacuum might not be the true ground state, that there could be a lower energy configuration the universe hasn't discovered yet. If true, the vacuum could suddenly transition to this lower state, releasing enormous energy and fundamentally changing the laws of physics in the process. This is called vacuum decay. And while it's highly speculative and considered unlikely, it's a possibility allowed by the mathematics of quantum field theory. The universe, it seems, might be sitting in a metastable state, like a ball balanced on a hill stable for now, but capable of rolling down if disturbed. Some find this unsettling, the idea that the vacuum itself could change, that the laws of physics are contingent on which vacuum state we happen to inhabit. But others find it exciting, a reminder that there's still so much we don't understand, so many questions left to answer. The quantum vacuum is not a passive stage on which particles play. It's an active participant influencing and being influenced, a sea of potentiality from which reality emerges moment by moment. As we drift here in this knowledge, contemplating particles that flicker in and out of being, forces mediated by ghosts, and a vacuum that seethes with hidden energy, it becomes clear that reality is far stranger than the solid, predictable world we perceive with our senses. At the quantum level, existence is fluid, probabilistic, interconnected in ways that defy classical logic. And yet, from this strangeness, from these fleeting phantoms and borrowed energies, emerges the stable, reliable universe we inhabit. A universe where stars shine, atoms bond, and life persists. What if the simple act of looking at something changed what it was? Not in a metaphorical sense, not psychologically, but physically, fundamentally altering its nature at the deepest level. You glance at a particle, and in that moment of observation, it transforms from a cloud of possibilities into a single, definite reality. Before you looked, it existed in multiple states simultaneously spread across space like a ghost. After you looked, it snapped into one location, one state, as if your awareness collapsed infinite potential into singular fact. This isn't philosophy. This is measurement in quantum mechanics. And it's one of the strangest, most debated aspects of reality, a puzzle that has haunted physicists for nearly a century, and still sparks fierce arguments about what the universe is, and whether consciousness plays a role in shaping it. The puzzle begins with something called the wave function, a mathematical object that describes a quantum system. If you have an electron, its wave function tells you the probability of finding it in different locations with different energies and different states. It doesn't tell you where the electron is, it tells you where it might be and how likely each possibility is. The wave function can be spread out across space, meaning the electron has some probability of being here, some probability of being there, and probabilities everywhere in between. Scientists call this a superposition, a state where the particle exists in multiple possibilities simultaneously. This sounds abstract, but it's been confirmed by countless experiments. The most famous is the double-slit experiment first performed with light in the early 1800s by Thomas Young, and later with electrons, atoms, and even molecules. Here's how it works. You fire particles, let's say electrons, at a barrier with two narrow slits. On the other side, you have a screen that lights up wherever an electron hits. If electrons were purely particles like tiny bullets, you'd expect them to pass through one slit or the other and create two bands on the screen, one behind each slit. But that's not what happens. Instead, you get an interference pattern, alternating bright and dark bands like ripples from two stones, dropped in a pond overlapping and creating areas where the waves reinforce and areas where they cancel out. This pattern appears even if you fire electrons one at a time, so slowly that only one electron is in the apparatus at any moment. Each electron doesn't just go through one slit or the other. It goes through both as a wave interfering with itself and only reveals where it landed when it hits the screen. The electron exists in a superposition of passing through both slits simultaneously until the moment it's detected. Research shows this isn't unique to electrons. Experiments have demonstrated interference patterns with photons, neutrons, atoms, and even large molecules containing hundreds of atoms. In 1999, researchers in Vienna sent buckyball spherical molecules made of 60 carbon atoms through a double-slit apparatus and observed interference. These are not subatomic particles. They're molecules large enough to see with specialized microscopes, yet they still exhibit quantum behavior, existing in superposition, behaving like waves until measured. Some believe the double-slit experiment reveals something profound about the nature of reality. It suggests that quantum objects don't have definite properties until they're measured. An electron doesn't have a position until you look for it. It doesn't travel through one slit or the other. It exists in a superposition of both paths, and only when it interacts with the screen, when a measurement occurs, does it collapse into a definite outcome. But here's where it gets even stranger. If you place detectors at the slits to determine which slit each electron passes through, the interference pattern disappears. Suddenly, the electrons behave like classical particles going through one slit or the other, creating two bands on the screen instead of many. The act of measuring which path the electron took destroys the superposition. It's as if the electron knows it's being watched and changes its behavior accordingly. This is the observer effect, and it's one of the most puzzling features of quantum mechanics. Measurement doesn't just reveal what's already there, it actively changes the system. Before measurement, the electron is in a superposition described by a wave function that includes all possibilities. After measurement, the wave function collapses to a single outcome. The electron is found in one place, not spread out over many. The wave becomes a particle. What causes this collapse? That's the measurement problem, and it's been debated since the 1920s. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg, says that the wave function represents our knowledge of the system, not the system itself. When we measure, we gain information, and the wave function updates to reflect that new knowledge. Before measurement, it's meaningless to ask where the electron is. It simply doesn't have a definite position. Measurement brings properties into existence. Einstein hated this interpretation. He thought it was absurd to suggest that reality depended on observation. In a famous debate with Bohr, he asked, "Do you really believe the moon isn't there when nobody looks?" Einstein believed in objective reality, a universe that exists independent of observers, and he thought quantum mechanics must be incomplete, missing some deeper layer of determinism. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, published a paper presenting what's now called the EPR paradox, arguing that quantum mechanics couldn't be a complete description of reality. The EPR argument goes like this. Imagine two particles that interact and then fly apart. Quantum mechanics says they can be entangled, meaning their properties are correlated in ways that can't be explained by them carrying definite values. If you measure one particle and find it spinning clockwise, the other will be spinning counterclockwise, even if they're light years apart. According to the Copenhagen interpretation, neither particle has a definite spin until measured. The measurement of one instantaneously collapses the wave function of both. Einstein found this spooky, as he called it, suggesting that either information travels faster than light, violating relativity, or the particles must have had definite spins all along, hidden from our view. He favored the latter, proposing that quantum mechanics was missing hidden variables, unknown factors that would restore determinism. For decades, this remained a philosophical debate. But in 1964, physicist John Bell devised a way to test it experimentally. He derived inequalities' mathematical limits on how correlated measurements could be if hidden variables existed. If experiments violated Bell's inequalities, it would mean hidden variables couldn't explain quantum mechanics. The universe really is fundamentally probabilistic. Research shows the experiments have been done many times with increasing sophistication. The first was by John Clauser and Stuart Friedman in 1972 using entangled photons. Later experiments by Alain Aspect in the 1980s and many others since have all reached the same conclusion. Bell's inequalities are violated. Quantum mechanics is correct. There are no hidden variables restoring classical reality. The correlations between entangled particles are stronger than any classical theory allows. The universe is non-local, meaning measurements here can instantaneously affect the state of a system far away, at least in terms of correlations. Einstein was wrong. Reality is stranger than he could accept. Have you ever wondered what this means for the nature of reality? If particles don't have definite properties until measured, what are they before measurement? Some interpretations say there are potentialities existing in a state of pure possibility. Others say they're vibrations in quantum fields, not localized objects at all. Still others propose radically different solutions to the measurement problem, each with its own philosophical implications. One alternative is the many worlds interpretation, proposed by Hugh Everett in 1957. According to this view, the wave function never collapses. Instead, every time a measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, you measure the electron at position A. In another, you measure it at position B. Both outcomes happen in different branches of reality, and you experience only one because your consciousness is tied to one branch. It's a solution that avoids the collapse problem, but at the cost of an infinite proliferation of parallel universes. Some find this interpretation extravagant, multiplying realities beyond necessity. Others find it elegant, preserving the linearity of quantum mechanics without introducing ad hoc collapse mechanisms. The truth is, we don't know which interpretation is correct, or if any of them are. The mathematics of quantum mechanics makes incredibly accurate predictions, but the meaning of that mathematics, what it says about the nature of reality, remains open to interpretation. There's another mind-bending experiment called the delayed choice quantum eraser, first proposed by John Wheeler and performed by researchers, including Yoon-Ho Kim in 1999. It takes the double-slit setup and adds a twist. You can choose whether to measure which path information after the particle has already passed through the slits, but before it hits the screen. The result? Your later choice determines whether the particle behaved like a wave or a particle in the past. It's as if the present can reach back and change history, though this interpretation is debated. What's clear is that the timing of measurement doesn't work the way classical intuition suggests. Scientists suggest these experiments show that quantum mechanics challenges our notions of causality, time, and separability. Events that seem space-like, separated too far apart for light to travel between them, can still be correlated. Choices made in the present seem to affect the past. Particles lack definite properties until the universe, or an observer or measurement apparatus, forces them to choose. The boundaries we draw between observer and observed, between here and there, between now and then, become blurred at the quantum level. There's a deep question lurking here about consciousness. Does observation require a conscious observer? Or is any physical interaction enough to collapse the wave function? Most physicists believe consciousness plays no special role, a particle detector, a photographic plate. Even a dust grain can cause decoherence, the process by which quantum superpositions become effectively classical. Decoherence happens when a quantum system interacts with its environment, becoming entangled with many particles. And this entanglement spreads the superposition so widely that interference effects vanish. You don't need a mind to collapse the wave function. Interaction with the environment does it. But a few physicists like Eugene Wigner and later Roger Penrose have speculated that consciousness might be fundamentally connected to quantum measurement. Wigner even proposed a thought experiment, Wigner's friend, where an observer watches another observer make a measurement, raising questions about when collapse occurs and who experiences it. These are minority views, highly speculative, but they illustrate how strange the measurement problem is and how it touches on questions usually reserved for philosophy and neuroscience. Research shows that decoherence, while it explains why we don't see macroscopic superpositions, like a cat being both alive and dead, as in Schrödinger's famous thought experiment, doesn't fully solve the measurement problem. Decoherence makes the interference effects unobservable by spreading them into the environment, but it doesn't explain why, when we look, we see one outcome rather than a superposition. It explains the appearance of collapse, but not collapse itself. The question of what happens during measurement, why one outcome is realized and not others, remains unresolved. Some interpretations, like the transactional interpretation or the pilot wave theory, offer different mechanisms. Pilot wave theory, originally proposed by Louis de Broglie and later developed by David Bohm, suggests particles do have definite positions, guided by a wave, and what we call randomness is actually deterministic but sensitive to initial conditions we can't know. It's a hidden variable theory that respects quantum predictions, but reintroduces determinism. However, it requires non-locality and other features that many find as strange as the Copenhagen interpretation. Light from collapse, certainty from superposition, reality from observation. What's undeniable is that measurement is different in quantum mechanics than in classical physics. Classically, you can measure something without disturbing it, at least in principle. Shine a dim light on a ball to see where it is, and the ball's motion barely changes. But quantum mechanically measurement fundamentally alters the system. To measure an electron's position precisely, you need to interact with it using a photon with short wavelength, which carries high momentum, and that photon kicks the electron, changing its momentum. The more precisely you measure position, the more you disturb momentum. This is the observational form of the uncertainty principle, but it goes deeper. Even in Gedanken experiments, thought experiments, where you imagine perfect non-invasive measurements, you still find that the act of measurement collapses the wave function. It's not just about practical disturbance from our clumsy instruments. It seems to be a fundamental feature of quantum mechanics that observation creates definite outcomes from indefinite potentials. There's an experiment that beautifully illustrates this called quantum Zeno effect, named after the ancient Greek philosopher Zeno and his paradoxes about motion. If you repeatedly measure a quantum system, you can actually freeze its evolution. Normally, a quantum state will change over time, evolving according to the Schrödinger equation. But if you measure it constantly, each measurement collapses the wave function back to its initial state, preventing it from evolving. It's like watching a pot and preventing it from boiling, except in quantum mechanics, the watching genuinely stops the process. This has been demonstrated experimentally with atoms and ions, showing that observation doesn't just reveal reality, it constrains it. Some believe these insights about measurement will be crucial as we develop quantum technologies. Quantum computers rely on maintaining superpositions of many qubits quantum bits that can be 0, 1, or both simultaneously. The challenge is preventing decoherence, keeping the system isolated from the environment, so the superpositions last long enough to perform calculations. Yet, eventually, you need to measure the result, collapsing the superposition to get an answer. Understanding and controlling measurement is key to making quantum computing work. Quantum cryptography also exploits measurement effects. In a protocol called quantum key distribution, Alice sends Bob photons in superpositions of polarization states. If an eavesdropper, Eve, tries to measure the photons to learn the key, she inevitably disturbs them, and Alice and Bob can detect the interference. The security of the system relies on the fact that measurement changes the quantum state, preventing perfect copying or eavesdropping. It's a practical application of the observer effect, turning a quantum quirk into a feature. As we drift here contemplating the strange dance between observer and observed, between potential and actual, it becomes clear that quantum mechanics doesn't just describe a universe of particles and waves. It describes a universe where reality is participatory, where the act of observation is woven into the fabric of existence. We are not separate from the cosmos, watching it from outside. We are part of it, and our interactions, our measurements, our observations help shape what becomes real. What if every quantum fluctuation, every random tremor in the fabric of space-time didn't just shape our universe, but created entirely new ones? What if the moment inflation began, it didn't stop everywhere at once, but continued in some regions, spawning pocket universes like bubbles in an infinite cosmic foam? Each bubble a separate cosmos, with its own laws, its own constants, its own story. Some too hot for atoms to form, others too cold for stars to ignite. And ours, this one, with its precise values and delicate balances. Just one possibility among infinite variations existing, not because it was designed, but because in an endless multiverse, every possibility must exist somewhere. We've followed quantum fluctuations from their birth in the void, through cosmic inflation, through the formation of galaxies and stars, through the strange world of virtual particles and measurement. But there's one more implication of these fluctuations, perhaps the most dizzying of all. If quantum fluctuations could trigger inflation, once creating our universe, why couldn't they trigger it again and again and again in an eternal process that never ends? This is the idea behind eternal inflation, and it leads to a conclusion that challenges everything we thought about: uniqueness, purpose, and our place in existence. The concept of eternal inflation was developed in the 1980s by physicists including Andrei Linde, Alexander Vilenkin, and Alan Guth. The core idea is simple but profound. During inflation, space expands exponentially fast. But quantum fluctuations mean that the inflatant field, the energy field driving inflation, doesn't have the same value everywhere. In some regions, it might decay, ending inflation and transitioning into the hot Big Bang that creates a universe like ours. But in other regions, fluctuations might push the field higher, causing inflation to continue. Those regions keep inflating, and within them more fluctuations occur. Some ending inflation locally, others sustaining it. Research shows this creates a fractal-like structure, a never-ending process where inflation stops in some places, creating bubble universes but continues in others, spawning more bubbles. Each bubble is a separate universe with its own beginning, its own evolution. They're causally disconnected. Light can never travel from one bubble to another because the space between them is inflating faster than light can cross it. We're inside one bubble, and there may be infinitely many others, each born from quantum fluctuations in an eternally inflating multiverse. Think of it like boiling water. Bubbles form, expand, and separate, each one distinct, surrounded by still boiling water that will eventually form more bubbles. Except in this analogy, the water is space-time, the bubbles are universes, and the process never stops. It's eternal, both into the future and possibly into the past, an infinite cosmic ocean of universes being born, existing, and perhaps eventually dying, all driven by quantum fluctuations. Some believe this solves one of the deepest puzzles in cosmology. Why is our universe so finely tuned for life? The laws of physics contain fundamental constants: the strength of gravity, the mass of the electron, the cosmological constant, and about 30 others. If these constants were even slightly different, the universe would be radically different. Stars might not form. Atoms might not be stable. Life, at least as we know it, would be impossible. For decades, physicists have marveled at this fine-tuning, sometimes called the Goldilocks problem. Everything seems just right. There are a few possible explanations. One is design some intentional force, set the constants to allow life. But most scientists find this unsatisfying because it doesn't explain anything. It just pushes the question back. Another explanation is necessity, maybe. The constants have to be what they are because of some deeper theory we haven't discovered yet. A theory that allows no other values. But we haven't found such a theory, and many physicists doubt it exists. The third explanation is the multiverse combined with the anthropic principle. If there are infinite universes with different values of the constants, then somewhere by pure chance there will be universes like ours, with the right conditions for complexity, stars, planets, and life. We find ourselves in such a universe not because it's special, but because we couldn't exist in the others. It's a selection effect. We observe a life-friendly universe because only life-friendly universes contain observers to do the observing. This is called the weak anthropic principle, and it's controversial. Some physicists embrace it as the most parsimonious explanation given eternal inflation. Others reject it as giving up on finding deeper reasons, as invoking an unobservable multiverse to explain what we see. The debate is ongoing, and it touches on philosophy as much as physics. What counts as a scientific explanation? Can we ever test the multiverse hypothesis if other universes are forever beyond our reach? Have you ever thought about what it would mean if the multiverse is real? It would imply that everything that can happen does happen somewhere. Every quantum possibility, every fluctuation, every branching of the wave function in the many worlds, interpretation, all realized in some universe. There would be universes almost identical to ours, differing only in tiny details. Others radically different with different forces, different particles, perhaps even different numbers of spatial dimensions. Research shows that in some versions of the multiverse, the fundamental laws themselves might vary. String theory. a candidate for a unified theory of quantum mechanics and gravity, predicts a vast landscape of possible vacuum states, each corresponding to different laws of physics. Estimates suggest there could be 10 to the 500 or more such states, an almost incomprehensibly large number. If eternal inflation is real and samples this landscape, then the multiverse would contain every possible set of laws allowed by string theory. Our universe, with its particular laws and constants, would be just one tiny corner of an unimaginably vast space of possibilities. This idea, called the string landscape, was developed by physicists like Leonard Susskind and Raphael Bousso in the early 2000s. It's built on the mathematics of string theory, which describes particles as tiny vibrating strings and requires extra dimensions beyond the familiar 3 of space and 1 of time. How these extra dimensions are curled up determines the effective laws of physics we observe. There are many ways to curl them, hence many possible universes. Some find this beautiful a theory that doesn't just explain our universe, but generates all possible universes, a kind of ultimate Copernican principle. We're not special, not central, not unique. We're one random sample from an infinite ensemble. Others find it frustrating because it makes certain predictions impossible. If anything can happen somewhere in the multiverse, how do we predict what should happen here? How do we test the theory? There have been attempts to make the multiverse testable, at least indirectly. One idea is to look for collisions between bubble universes. If our universe formed in an eternally inflating space and other bubbles formed nearby, they might have collided with ours before inflation ended. Such a collision would leave a mark on the cosmic microwave background, a disc-shaped region with unusual temperature or polarization patterns. Researchers have searched for these signatures in CMB data from Planck and other satellites. So far, nothing definitive has been found, but the search continues. A single collision scar would be smoking gun evidence for the multiverse. Another approach involves studying the statistical distribution of physical constants. If we're a random sample from a multiverse, we should be typical in some sense. This leads to predictions about how likely certain values of constants should be. For example, the cosmological constant dark energy is much smaller than quantum field theory naively predicts, but not zero. In a multiverse, regions with very large cosmological constants would inflate so fast that galaxies couldn't form, while regions with negative values would collapse too quickly. Only a narrow range allows structure in life. We should expect to find ourselves in that range, and indeed we do. This is sometimes cited as evidence for the multiverse, though it's far from conclusive. Scientists suggest that the multiverse might also explain why inflation happened in the first place. In a single universe, you have to fine-tune the initial conditions to get inflation started. But in an eternally inflating multiverse, inflation is always happening somewhere, and quantum fluctuations ensure it starts in new regions constantly. There's no need for special initial conditions because the multiverse is eternal, with no beginning. It's always existed, always will exist, self-perpetuating through quantum fluctuations. This raises profound questions about time and causality. If the multiverse is eternal, does it make sense to ask what caused it? Or is causation only meaningful within a universe, not for the multiverse as a whole? Some cosmologists like Alexander Vilenkin argue that even an eternal multiverse must have had a beginning, based on mathematical theorems about the impossibility of past eternal inflation. Others like Alan Guth think the multiverse might genuinely be past eternal, avoiding the need for a first cause. Light from infinity, meaning from vastness, home in randomness. There's a deep philosophical tension here. On one hand, the multiverse seems to rob the universe of meaning. If everything happens somewhere, does anything matter? If there are infinite versions of you making every possible choice, does choice itself become meaningless? On the other hand, the multiverse can be seen as ultimate possibility. A universe or set of universes so rich, so varied, that every potential is actualized. From this perspective, it's not a loss of meaning, but an expansion of it. Some physicists take a middle path. suggesting the multiverse is a natural consequence of our best theories, quantum mechanics and general relativity applied to cosmology. And whether we like the implications is irrelevant. Science isn't about comfort. It's about following the evidence and the mathematics wherever they lead. If eternal inflation is correct, and if it leads to a multiverse, then that's the reality we inhabit whether we find it meaningful or not. There's also the question of what counts as a universe. In the many worlds interpretation of quantum mechanics, every measurement splits reality into branches, creating a multiverse of a different kind. Not separate bubble universes in space, but separate branches of the wave function. These branches are all part of the same quantum state, just evolving along different trajectories. Some physicists like Max Tegmark have proposed a hierarchy of multiverses, distinguishing between different types. The quilted multiverse of distant regions beyond our cosmic horizon. The inflationary multiverse of bubble universes, the many worlds. Multiverse of quantum branches, and even a mathematical multiverse where every consistent mathematical structure exists as a universe. Research shows that distinguishing between these types is important because they have different implications and different levels of speculation. The quilted multiverse is almost unavoidable. If space is infinite, there must be regions beyond our horizon. And if space is truly infinite with finite possible states, then every configuration repeats infinitely often. The inflationary multiverse is a prediction of eternal inflation, which is well motivated by our understanding of quantum fields and cosmology. The many worlds multiverse follows from taking quantum mechanics seriously without adding collapse. The mathematical multiverse is highly speculative, more philosophy than physics, but it raises interesting questions about the nature of existence in mathematics. Do you ever wonder if there's another version of you somewhere in the multiverse making different choices? In the many worlds interpretation, there certainly is infinitely many versions. In fact, one for every quantum outcome that affects your brain and decisions. In the inflationary multiverse, if the bubbles sample different laws of physics, there might be universes where beings vaguely like you exist. But the differences would be so vast that it's hard to say if they're really you in any meaningful sense. These questions touch on identity continuity and what it means to be a person. If there are infinite copies of you, are they you? Or are they separate beings who happen to share your past? Up to some point, philosophers have debated personal identity for centuries, and the multiverse adds new layers of complexity. It's an area where physics meets philosophy and clear answers are elusive. One practical consequence of multiverse thinking is that it changes how we approach certain problems in physics. If we're trying to explain why a constant has a particular value and the multiverse is real, the answer might simply be anthropic selection. That's the value we observe, because other values don't allow observers. This can feel like giving up, but it might also be the truth. Not every question has a deeper answer. Sometimes the explanation is contingency, not necessity. Some believe this is already happening with dark energy. Its value is extraordinarily small, about 10 to the minus 120 in certain units, far smaller than any natural scale in particle physics. Why so small? No known principle explains it. But in a multiverse, most regions would have larger or smaller values, and only in a narrow range would galaxies form, allowing life to ask the question. This anthropic reasoning has led some physicists to accept the cosmological constant as an environmental constant, varying from universe to universe rather than a fundamental one fixed by deep laws. Yet, not everyone is convinced. Critics argue that invoking the multiverse is a retreat from the goal of physics to find unique testable explanations for why the universe is the way it is. If we can explain anything by saying it's different in other universes, we lose predictive power. The theory becomes unfalsifiable, more metaphysics than science. This criticism has merit, and it's why many physicists remain skeptical of the multiverse despite its theoretical appeal. There's also the measure problem in eternal inflation. If there are infinitely many universes, how do we assign probabilities to different outcomes? Infinity is tricky. If there are infinitely many universes of type A and infinitely many of type B, which is more common, the answer depends on how you count on how you define a measure over the infinite set. Different measures give different predictions, and we don't know which, if any, is correct. This is an active area of research, and until it's solved, eternal inflation remains incomplete as a predictive theory. Light from question, wonder from vastness, humility from infinity. As we rest here drifting through the implications of quantum fluctuations taken to their ultimate extreme, universes, born from fluctuations, multiverses from eternal inflation, infinite possibility from quantum randomness, it becomes clear that the cosmos is far larger, far stranger, far more generous with existence than we ever imagined. Whether the multiverse is real remains an open question, one that future observations and theoretical developments may settle. But the journey to this question, from the first tremor in the void to the eternal proliferation of universes, is a testament to the power of quantum mechanics to reshape our understanding of reality. We've traveled far together, from the very first instant of creation to the edge of infinity itself. We've watched quantum fluctuations emerge from pure uncertainty stretch across the cosmos during inflation and imprint themselves on the ancient light that surrounds us. We've seen how these tiny tremors became galaxies, stars, and worlds. We've explored virtual particles flickering in and out of existence, the strange dance of measurement and collapse, and even the possibility that our universe is just one bubble in an endless cosmic foam. But now, as we drift toward the end of this journey, there's one question left to answer, the most personal one of all. What does any of this have to do with you? Right here, right now, breathing quietly in the darkness. The answer is everything. Absolutely everything. You are not separate from this story. You are the story. Every atom in your body, every particle that makes you who you are, traces its lineage back to those first quantum fluctuations in the void. The calcium in your bones was forged in a star that existed because quantum fluctuations created regions of slightly higher density 13.8 billion years ago. The iron in your blood came from a supernova explosion, and that star only formed because gravity had something to pull on matter that gathered in patterns determined by quantum randomness during inflation. The oxygen you breathe, the carbon that forms the backbone of your DNA, the hydrogen that makes up most of your body's mass, all of it connects back to the trembling void, to the uncertainty principle, to the quantum dance that has never stopped. Research shows that quantum mechanics isn't just ancient history, something that mattered only in the first moments after the Big Bang. It's happening now constantly at every level of reality. The chemical bonds that hold your molecules together exist because of quantum mechanics. Electrons and atoms don't orbit like planets around the sun. They exist in clouds of probability. Their positions uncertain until measured, their behavior governed by wave functions and superpositions. The very stability of matter. The reason you don't collapse into a point or evaporate into energy depends on the uncertainty principle, giving particles a quantum fuzziness that prevents catastrophic collapse. Even your senses rely on quantum processes. Vision begins when photons, quantum particles of light, strike molecules called rhodopsin in your retina. These molecules change shape when hit by a single photon, triggering a cascade of chemical reactions that eventually becomes a neural signal, an electrical pulse traveling to your brain. You can detect individual photons, individual quanta of light. Your eyes are quantum detectors, sensitive enough to register the smallest unit of electromagnetic energy. Some studies suggest that under ideal conditions, humans can perceive as few as 5 to 7 photons. We are quantum-sensitive beings living in a quantum universe. Scientists suggest that quantum effects might play roles in biology we're only beginning to understand. Photosynthesis, the process plants use to convert sunlight into chemical energy, appears to use quantum coherence, maintaining superpositions of energy states to transfer energy with remarkable efficiency. Birds may navigate using quantum entanglement in molecules in their eyes, sensing Earth's magnetic field through quantum processes. Even the sense of smell might involve quantum tunneling, where the shape of molecules alone doesn't determine scent, but rather electrons tunneling through molecular bonds create distinct vibrational signatures we perceive as different smells. These are areas of active research not yet fully confirmed, but they hint that quantum mechanics isn't confined to physics labs. It's woven into life itself. Think about that for a moment. You might be using quantum entanglement to find your way home, quantum coherence to see colors, quantum tunneling to smell a flower. The boundary between the quantum world and the everyday world is far blurrier than we once thought. We are not classical beings living in a quantum universe. We are quantum beings through and through, made of particles that exist in superpositions that tunnel through barriers that respond to the fundamental uncertainty built into existence. There's something profound in this. For most of human history, we've felt separate from the cosmos, small, isolated, looking up at stars that seemed impossibly distant and alien. But quantum mechanics tells a different story. It says you are made of the same stuff as stars, governed by the same laws, connected to the same quantum fields that permeate all of space. The electrons in your brain are indistinguishable from electrons in distant galaxies. The photons you see were created by the same quantum processes that created light in the first moments after the Big Bang. You are not in the universe. You are the universe experiencing itself, a local concentration of complexity and awareness that emerged from quantum fluctuations billions of years ago. Research shows that this connection goes even deeper. If the many worlds interpretation is correct, every quantum event in your body creates branches of reality. Every time a particle in your brain could be here or there, every time a neural signal could fire or not fire, based on quantum probabilities, the universe splits. There are versions of you experiencing every possible outcome of every quantum event. This sounds overwhelming, perhaps even meaningless, but some physicists find it liberating. It means that in a very real sense, every version of you exists. Every path is taken, every possibility realized somewhere in the vast tree of branching realities. Even if you don't accept many worlds, the implications of quantum mechanics for personal existence are striking. Your thoughts, your consciousness emerge from the firing of neurons, which depends on the flow of ions through channels in cell membranes, which is governed by quantum mechanics. The particular sequence of thoughts you're having right now, the fact that you're listening to these words, understanding this, ideas, all of it rests on quantum processes, on particles that exist in superposition until they interact on fields that fluctuate according to the uncertainty principle. Consciousness itself, whatever it is, emerges from a quantum substrate. Some researchers like Roger Penrose and Stuart Hameroff have even proposed that consciousness might involve quantum coherence in structures called microtubules within neurons, though this remains highly controversial and unproven. What's certain is that the brain is not a classical computer. It's a quantum system. And while decoherence happens quickly in warm, wet environments like living tissue quantum effects still matter. The exact role they play in cognition and consciousness is one of the great unsolved questions at the intersection of physics, neuroscience, and philosophy. Have you ever felt a moment of pure awareness where you're conscious of being conscious, thinking about thinking? In those moments, you're a quantum system reflecting on itself. Matter and energy arranged in patterns that allow the universe to know it exists. It's as close to magic as physics gets, not supernatural magic, but the deep magic of emergence complexity arising from simplicity, awareness from atoms, meaning from mathematics, light from matter, thought from tremors, self from stars. There's a concept in cosmology called the cosmological principle, which says that on the largest scales, the universe is homogeneous and isotropic, the same in all places and in all directions. But we've learned that this smoothness emerged from quantum fluctuations, from tiny variations that grew into the structure we see. In a similar way, human life emerges from quantum randomness, the particular arrangement of atoms that makes you unique, the specific DNA sequence you carry, the exact pattern of neural connections in your brain, all shaped by countless quantum events, mutations caused by cosmic rays, striking DNA chemical reactions, proceeding via quantum tunneling neural pathways, forming through processes with inherent quantum uncertainty. You are, in a very literal sense, a child of chaos. Not chaos in the sense of disorder, but chaos in the mathematical sense, sensitivity to initial conditions, determinism at the macro scale emerging from randomness, at the micro scale patterns forming from noise. Quantum fluctuations ensured that no two people are identical, that each of us is a unique experiment in what matter can become, what consciousness can experience. Without quantum mechanics, without the uncertainty principle, the universe would be deterministic, predictable, dead, in a sense. Quantum randomness is what allows novelty, creativity, the genuine emergence of new patterns that couldn't be predicted from initial conditions alone. Research shows that this randomness is fundamental, not just a gap in our knowledge. Einstein hoped for hidden variables, for a deeper determinism underlying quantum mechanics. But experiments testing Bell's inequalities proved him wrong. The universe is genuinely probabilistic at its core, and from that probabilism comes freedom, not free will in the philosophical sense, which is still debated, but freedom from total predictability. The future is not written. It emerges moment by moment from the quantum dance of particles and fields, including those in your brain. Some find this unsettling. If the universe is fundamentally random, does anything matter? But randomness doesn't mean meaninglessness. It means openness. It means the future is genuinely undetermined, that there's space for possibility, for change, for things to be different than they were. The same quantum fluctuations that shaped galaxies also shape your choices, your experiences, your life. You are not a passive observer of a predetermined script. You are an active participant in an unfolding story, one where the next page hasn't been written yet, because it's being created now through quantum processes happening in your brain and body. There's a beauty in this that's hard to express. We've spent this entire journey exploring quantum fluctuations in the cosmos, vast, impersonal, mathematical. But those same fluctuations are also intimate, personal, immediate. They're happening in you. The trembling void that created the universe is still trembling in the atoms of your body, in the neurons of your mind. You carry the cosmos within you, not metaphorically, but literally. Scientists suggest that in about 100 trillion years, if current cosmological models are correct, the last stars will burn out. Galaxies will have long since dispersed. Black holes will have evaporated via Hawking radiation, and the universe will be cold, dark, and nearly empty. But even then, even in that distant, desolate future, quantum fluctuations will continue. The vacuum will still tremble. Virtual particles will still flicker in and out of existence. The universe will never be truly still, truly empty. The quantum nature of reality ensures that something always stirs, that nothingness is impossible. But long before that unimaginably distant future, there is now. There is you here, experiencing this moment. And this moment, like every moment, is a gift from quantum fluctuations. The fact that you exist, that you're conscious, that you can understand these ideas and feel wonder at the universe, all of it, traces back to the first tremor in the void, to the uncertainty principle making stillness impossible to inflation, stretching quantum ripples across the cosmos to billions of years of structure formation and stellar evolution and chemical processes and biological evolution, all of which depended on quantum mechanics at every step. You are 13.8 billion years of quantum history embodied. You are stardust, yes, but you're also quantum foam given form and awareness. You're a way for the universe to know itself, to explore its own possibilities, to ask questions about where it came from and where it's going. And the answer to those questions always leads back to quantum fluctuations, to the tiny ripples that shaped everything. Light from darkness, form from fluctuation, wonder from uncertainty. As we come to the end of this journey, I want to thank you for drifting with me through these quiet explorations of the quantum cosmos. We've traveled from the void to the multiverse, from virtual particles to cosmic structure, from the uncertainty principle to the edge of knowledge itself. These are not easy ideas. They challenge our intuitions, our sense of what's real, our place in existence. But they're also beautiful, perhaps the most beautiful ideas humanity has ever discovered, that the universe emerged from quantum randomness, that nothing is ever truly still, that you are connected to everything through the same quantum fields and fluctuations that created galaxies. I hope you'll carry this with you. The next time you look at the stars, remember they exist because of quantum fluctuations. The next time you feel lost or small, remember you're made of atoms forged in stellar cores, assembled through quantum processes, part of an unbroken chain of causation, stretching back to the first instant of time. The next time you wonder if you matter, remember that you are the universe looking at itself, asking questions, seeking understanding. That is not nothing. That is everything. Rest well, knowing that the cosmos trembles within you. Dream gently, carried by the same quantum currents that shaped reality itself. And know that the story continues. It always continues in every atom, every moment, every breath. Sleep well, dream gently. The universe remembers. Good night. Thank you for staying with me through this cosmic journey. There are more stories to tell, more mysteries to explore softly in the darkness. Until the next quiet night finds you again, rest easy in the knowledge that you are exactly where you're meant to be. A quantum fluctuation that learned to wonder, a tremor that became aware, a child of the cosmos coming home to itself.